A whisper fills the universe, softer than starlight, older than any cluster or comet, patient as frost settling on a window at dawn. It washes through empty gulfs, where no sun has yet struck a planet, where no listener waits, yet it remains, unwavering. This whisper is not sound, yet it carries rhythm. It is not wind, yet it drifts everywhere. It is a glow cooled to near silence, a bath of ancient light that once burned brighter than any furnace, yet now rests at a temperature that invites quiet. It is the cosmic microwave background, the most relaxed conversation the cosmos ever had with itself, still ongoing, still gentle. Picture a night with no moon and no street lamps, the kind of darkness that teaches the eyes to widen and the mind to slow. Through that darkness, imagine a light so pervasive that nothing could hide from it, yet so faint that no human eye can see it unaided. The sky is filled with it, horizon to horizon, corner to corner, inside every window of every galaxy. The universe glows not with neon, not with flame, but with the aftertaste of its own birth, transformed from a roar to a hush. The light is smooth, so smooth that it could be mistaken for perfect stillness, like a lake that refuses to ripple. There is great comfort in the idea that the whole sky, at every hour, in every direction, carries the same quiet temperature, about 2.725 Kelvin, a number that reads like a sigh, not a shout. It sits just above absolute zero, a place where motion almost ends, where atoms slow their dance to the edge of freezing thought. That single number tells a story about the way time stretches, about how heat becomes history. The light that reaches every radio dish and every microwave antenna is not frantic. It is patient, wearing down the sharpness of creation into a rounded lull. This glow carries the signature of a black body, the most honest spectrum that nature knows. No peaks from excited atoms, no ornate lines carved by elements, only the curve of perfect balance between energy and emptiness. The curve arches softly, a long hill of wavelengths peaking in the microwave band, around millimeters in scale, then easing away into radio quietude. A black body is what a perfect furnace would sing if it had no walls, and the universe once came close to that perfect furnace. Now that song is transposed into a key that no human ear hears, yet every calm mind can imagine. The light has been stretched by the growth of space itself. Each photon has ridden the slow expansion, lengthening as the universe lengthened, cooling as the cosmos exhaled. The idea feels like a deep breath released across billions of years. No hurry, no struggle, just the mathematics of distance increasing, the wavelength drifting longer, the temperature sliding downward with quiet persistence. This is relaxation not as a mood, but as a physical law, a transformation conducted by the fabric of reality. The result is a background that is everywhere and nowhere in particular, a presence that speaks without intruding. Tuning an old television in an empty cabin, one might have seen static, a flutter of snow on glass, a portion of which was this same ancient glow. It was a domestic brush with cosmology, the universe tapping on a household screen. The crackle was not menacing. It was the cozy evidence that the largest possible thing also lives in the smallest living rooms. The background is inclusive in this way. It asks no permission, and it shows no preference. Galaxies drift, stars flare and die, planets ripple with weather, yet through it all this light remains a constant companion, like a heartbeat heard through a pillow. Calm does not mean empty. The glow holds memory. It remembers an epoch when everything was close, when light could not travel far without meeting charged particles that would scatter it like sunlight in fog. Then came clarity, when the universe aged enough to cool and allow electrons to nestle into orbits, forming neutral atoms, and the fog lifted. The light set free in that clearing has travelled ever since, crossing a growing stage, losing energy to the expansion, gaining serenity in exchange. The memory it carries is not a list of events, but a texture of conditions, a fingerprint smoothed by time yet still traceable by thoughtful hands. This faint radiance brings a lesson in humility. The color of the glow, though invisible to the eye, defines a baseline for everything that shines. Against it, stars are embers, galaxies are lanterns, quasars are searchlights, yet the background is the floor upon which all this brilliance stands. Remove the fireworks, remove the spotlights, and this floor remains, a soft carpet of ancient warmth. That familiarity is soothing. It tells that the universe did not forget its beginnings. It preserved them, cooled them, and offered them to anyone who cares to listen. The comfort grows deeper when the near uniformity of this light is considered. The sky looks the same to this glow wherever one points a well-tuned instrument. The sameness is not sterile, it is maternal. Near uniformity suggests that the cosmos once shared conditions to an extraordinary degree, making every place kin to every other place. In that kinship lies a form of peace. No corner rages alone. No edge hoards all the heat. There is balance, not forced, but baked in by the early story of space and time. The glow also brings scale into comprehension. Millimeter wavelengths, microkelvin deviations, billions of years of travel, a temperature just above zero, a horizon measured not in miles or light years, but in the curvature of space itself. These numbers are cool to the touch, devoid of panic. They are the vocabulary of a universe in repose. To recite them is like naming constellations. The mind slows, aligns with patterns, and rests on the structure beneath spectacle. Every relaxed room has a hum, the quiet vibration of systems at equilibrium. The cosmic microwave background is the hum of the largest room. It is the music of an engine that started hot and has settled into a low, idle, steady, and trustworthy. This hum does not command attention, it rewards curiosity. When noticed, it changes the atmosphere of thought, replacing urgency with patience, replacing noise with signal, replacing isolation with context. The listener becomes a participant in an old conversation, one that does not press, one that does not end. There is a meditative quality in knowing that the same photons glide through the vastness and pass through bodies at this moment. They touch skin without harm, slip through bone without resistance, and carry onward, indifferent yet intimate. The connection is not mystical, it is physical. The universe is not somewhere else. It is here, bathing every surface with the residue of its own earlier heat. To be warmed by a star is common. To be brushed by the oldest light is a gentler intimacy, a reminder that existence is not merely dramatic events, but continual presence. In the night of the mind, when headlines quiet and tasks fade, there remains an awareness that everything shares a background. The cosmic microwave glow is a literal background, a fixed field against which the actors move. It is also a metaphor done right, grounded in physics, not in wish. That makes it uniquely calming. It does not promise happiness, it demonstrates endurance. The light neither argues nor persuades. It testifies, with infinite patience, that the universe once burned, that it now breathes, that time can be a softening force. To contemplate this glow is to practice a physics of ease. It encourages questions that do not clamour. What kind of place lets relic light fill it so completely, yet lets galaxies carve story upon story in front of it? What kind of laws allow heat to cool without malice, structure to form without haste, backgrounds to persist without slipping into oblivion? The answers are not urgent. They arrive with the same tempo as the glow itself, steady and fair. The sky looks empty to the hurried eye. To the patient eye, it glows with the oldest consolation, a field of warmth stretched thin yet never broken. The cosmic microwave background is the calm that follows the storm, the candle that remains after the bonfire, the enduring low chord beneath the symphony of stars. In that chord, the universe invites reflection. In that softness, it becomes a kind of home. The story opens in a field of grass above a quiet New Jersey road, where a pale structure points at the sky with the patience of a lighthouse. It is the Holmdel horn antenna, a smooth metal funnel attached to a reflecting sheet, built to cradle radio waves with care. The instrument was designed to speak with human satellites and to keep terrestrial noise at bay. Its geometry offered two virtues at once. It accepted the heavens with wide arms and let unwanted echoes fall away. Into this stillness stepped two radio engineers, Arno Penzias and Robert Wilson, bringing method, curiosity, and the habit of listening longer than most people care to wait. They began with a radiometer that measured in centimeters, a frequency near 4 gigahertz where the sky is usually quiet. The plan was simple: understand the instrument so well that any whisper from above could be trusted. They calibrated by pointing at a region of sky believed to be dim. They compared it to a reference load chilled to the temperature of liquid helium. Every decibel mattered. Every joint needed to be understood. The horn was aligned so that the ground and nearby structures would not foul the measurement. They knew that the instrument could add its own warmth to the signal. They measured that too. Patience and arithmetic would be the remedy. Yet the numbers refused to relax all the way down. Even after accounting for warm electronics and known backgrounds, a residue clung to the measurements. It was small but stubborn, about 3 Kelvin above the expected floor. They hunted for culprits with a calm determination. Could New York City glow into the side lobes? They checked by turning the antenna. The excess did not change. Could the Milky Way be the source? They mapped different latitudes. The surplus remained. Could it be the Sunday? They watched for seasonal and daily shifts. The value held steady. The instrument insisted that the sky possessed a uniform warmth that did not care where the horn was aimed. They found pigeons living in the antenna, cooing in the metal rafters as if the structure were a modern bell tower. The birds left a pale layer inside the horn, a thin film of unwanted dielectric. The engineers removed the nests and scrubbed the interior, then waited for the numbers to improve. The radiometer continued to report the same soft surplus. They recalibrated. They cooled components again. They listened through winter and into summer. The excess stayed. It behaved like a footprint stamped onto space itself. Not far away, a group at Princeton was chasing a theoretical prediction about relic radiation from a hot early epoch. Robert Dick, Jim Peebles, Peter Roll and David Wilkinson had built a new instrument to find the afterglow of a dense young universe. The idea had a lineage. Years earlier, George Gamow, Ralph Alpha, and Robert Herman had predicted that a universe born hot would leave behind a cooled microwave remnant. The expected temperature had been estimated in the single digits above absolute zero. The concept had drifted in and out of focus in the community, sometimes mentioned and sometimes set aside. The Princeton team revived it with fresh calculations and an experimental plan. Their instrument was approaching readiness. Penzias and Wilson did not begin with this cosmological expectation. Their task was to purify a communication instrument and to understand the sky at centimeter wavelengths. When their persistent surplus refused to vanish, they reached out to colleagues to discuss the puzzle in plain technical terms. Word travelled across telephone lines and through conversations in offices where chalk dust could still be seen. The connection between the Holmdel signal and the Princeton search slowly clarified. If the universe were filled with relic microwave light, it would appear as a uniform temperature added to every line of sight, exactly the kind of gentle surplus neither city nor galaxy could explain. A meeting followed between the two teams. The Holmdel engineers described the excess in careful detail. They emphasized the extensive corrections for instrument noise and the diligence of their surveys across the sky. The Princeton group recognized the signature of the relic background in the description. In that recognition lay an elegant resolution. The surplus did not belong to the horn. It belonged to the cosmos. 2 papers would soon appear. One presented the observation of a uniform microwave background at a few Kelvin across the sky. The other provided the theoretical framing and experimental context that made sense of the finding. Together they offered a doorway into cosmic history that could be walked through with measurements rather than metaphors. The Holmdel horn had been made to aid conversations with orbiting reflectors, yet it possessed qualities that made it an ideal listener to the sky. Its low side lobes suppressed stray radiation from the ground. Its stable platform allowed precise calibration. Its environment was quiet enough to keep human noise from overwhelming faint signals. The choice of frequency by Penzias and Wilson lands in a sweet region where the atmosphere is transparent and galactic synchrotron emission is moderate. The instrument had the right temperament to cradle the small and the subtle. What the radiometer measured can be translated into a temperature because radio waves carry energy that instruments convert into a thermodynamic language. Antenna temperature becomes a way of saying how much the sky warms the receiver. A few Kelvin might sound negligible when compared with laboratory warmth, but for radio astronomy it is the difference between absence and presence. The meticulous subtraction of known contributions is an art as much as a science. The stability of the answer after every correction is the sign that the measurement has touched something real. The setting of the discovery is instructive. A grassy hill in a state better known for highways and towns became the vantage point for an encounter with the universe at large. The protagonists were not cloistered theorists nor flamboyant explorers. They were engineers who honoured detail and followed evidence. Their work unfolded in an age when communication satellites were new and radio astronomy was becoming a mature field with tools that favoured patience over spectacle. The cosmic signal did not arrive with fanfare. It arrived as a mild insistence that refused to be wished away. This detection shifted the centre of gravity in cosmology from speculation to measurement. It introduced a background against which models would be tested. It told experimenters where to point and what to build. The signal in centimetres offered not only proof of a hot early era, but also a promise that finer features might be hidden within the uniform glow. That promise would motivate generations of instruments designed to map small fluctuations and to test ideas about how the earliest moments unfolded. The cornerstone began with a surplus of a few Kelvin that would not disappear under a cloth of excuses. Recognition followed. The engineers who refused to ignore the excess were honoured for revealing a relic that belonged to everyone. The antenna itself became a monument, a quiet sculpture to listening. The phone conversations and seminars that tied Holmdel to Princeton added a graceful note to the history. Independent approaches met in the middle. Practical attention to unwanted noise met theoretical attention to ancient light. The convergence of methods gave strength to the claim. The trace of pigeons, the cold loads, the careful sweeps of the sky, the clear statement of uncertainty in error bars, all contributed to a discovery that transformed a subtle signal into a pillar of understanding. The temperature that seemed like a nuisance became the key. The excess became a fingerprint. The horn on the hill became a cosmic stethoscope, hearing the lowest pulse the universe emits. The act of discovery here was not a sudden spark. It was a sustained gaze that allowed a truth to come forward at its own pace. A listener can imagine the last twist of a valve, the quiet click of a switch, the look toward a meter that refuses to drop that final fraction. There is serenity in that image. The sky speaks softly, and patient instruments answer softly. The story of this detection is a reminder that the immensity of the cosmos does not always arrive through thunder. Sometimes it arrives when a pair of listeners clears a nest, steadies a pointer, compares against a colder piece of metal, and then admits that the warmth is not theirs to remove. Calm light can deliver a quiet jolt. The glow that fills the sky seems uneventful at first glance, yet its very character unsettles expectations. A field that cool, that even, that pure, presents a paradox wrapped in comfort. The first surprise lives in its uniformity. Nearly every direction reveals the same temperature, within tens of microkelvin, a sameness so complete that it strains the idea of distant regions evolving independently. If far apart patches of the young cosmos could never have exchanged messages at the speed of light, how did they coordinate so precisely? The horizon that limits communication appears too small to have permitted such agreement. Yet, agreement is written across the entire sphere. The light looks like a painting executed by a single hand, even though the canvas was split into areas that should not have consulted one another. The next surprise is spectral. The curve of its brightness as a function of frequency forms a blackbody with a precision that no ordinary furnace could match. There are no sharp lines from intervening atoms, no bumps that betray stray energy injections, no scars from messy astrophysical processes. It is as if the radiation was pressed flat by thermal equilibrium so thorough that later epochs failed to wrinkle it. A laboratory spectrum might achieve comparable neatness under controlled conditions, but nature rarely offers this level of ideality. The universe appears to have thermalized itself in its youth, with an efficiency that leaves almost no room for afterthoughts. A hot, dense origin becomes more than a story. It becomes a measurement, and the certainty of that measurement is surprisingly gentle. Small deviations from the average do exist, but they arrive with another unexpected quality. They are tiny, at a level of 1 part in 100,000. Such subtle freckles raise a question of balance. Structure requires seeds, yet too many seeds would smear the spectrum and erase the blackbody grace. The numbers settle at a compromise that seems delicately tuned. The initial ripples are large enough to grow into galaxies and clusters under gravity, but small enough to keep the background nearly uniform. The surprise is not only that this balance exists, but that it points to specific conditions in the early plasma, where radiation pressure and gravity traded influences with exquisite timing. Motion adds a gentle twist. A single large dipole pattern imprints itself on the sky because the observer drifts through the background. The entire spectrum appears slightly warmer in the direction of motion and slightly cooler behind. This is ordinary relativity applied to low-energy light, yet the precision of the dipole's amplitude and direction provides a strangely intimate measurement of a planet's velocity within a vast web. A global thermometer becomes a speedometer. That is an elegant shock, the realization that a local journey can be read from a universal field. Geometry enters the conversation with quiet authority. The angular scale of the first acoustic crest in the pattern of temperature variations implies a spatial curvature that is remarkably close to zero. In other words, space appears flat to high accuracy across volumes that defy intuitive scale. A flat geometry is not the only option in general relativity, yet the data keep pointing to this outcome. The shock hides behind the calm phrasing. The largest structure one can imagine looks as if a straight line remains straight forever, with only tiny tolerated deviations. The visible ripples become a ruler for cosmic shape, and the ruler says that the stage is neither closed like a sphere nor open like a saddle to any obvious degree. Flatness is not a default for arbitrary initial conditions, so its persistence invites deeper reasoning. Chemical history leaves another quiet astonishment. The lack of spectral distortions suggests that any significant energy injections after the first few 100,000 years were tightly constrained. Had violent processes heated the background later, they would have carved Mi or Y-shaped departures in the spectrum. The absence of such features implies a narrative of relative tranquility for the background once atoms formed. Stars and black holes can be fierce, yet their collective influence on this particular glow remains remarkably mild. The universe built drama without rumpling its oldest light beyond recognition. The balance between radiation and matter introduces a further surprise in the measured heights and spacings of the acoustic peaks. The pattern implies a particular ratio of ordinary baryonic matter to total matter, and a density of dark matter that exerts gravity without sharing the electromagnetic dance. The background acts like a resonant drum that remembers how much weight sat upon it. That memory points toward unseen mass shaping the rhythm. To infer an invisible component from a relaxed glow feels counterintuitive, yet the inference is consistent across independent measurements. The background does not shout about dark matter. It whispers it, with characteristic scales that align with the growth of structure seen later. Neutrinos drift through this tale as ghostly participants. Their presence and number alter the pace of the early expansion and the propagation of waves in the primordial plasma. The subtle smoothing of the smallest scales and the phase of the oscillations encode the influence of these light particles. The background becomes a census taker for entities that barely interact. The shock lies in the delicacy of the constraint. A field that relaxes so completely still manages to carry precise information about particles that pass through matter almost without acknowledgement. Time itself is instructed by the glow. The rate at which the universe expands today leaves an imprint on the angular scale of features formed long ago. Calibrating local distance ladders and comparing them to the scale inferred from the background can lead to a quiet discord. The disagreement over the present expansion rate, though not violent, is persistent enough to suggest that something subtle might be missing from the ledger. A calm field becomes a sensitive auditor, revealing either overlooked systematics or hints of new physics. The surprise is that a very old light can critique measurements made with modern candles and galaxies. Foregrounds, the local veil of dust and charged particle radiation in a home galaxy, also carry a twist in this context. The fact that they can be removed to reveal microkelvin patterns beneath demonstrates not only instrumental skill, but the astonishing stability of the background signal. The very possibility of separating cosmic from local contributions depends on the background being smooth and well described. That clarity was not guaranteed. The sky could have been messy at these wavelengths in ways that obscured the relic field. Instead, the background stands available, ready to be peeled free with care, like a perfectly preserved fresco beneath later paint. All of these shocks share a personality. None arrives with thunder. They arrive as corrections to intuition that lean toward elegance. It becomes clear that the glow is not merely leftover heat. It is a ledger of conditions written in a script of smoothness, punctuated by tiny, informative deviations, thermal equilibrium so complete that a perfect spectrum emerges. Horizon-scale coordination that begs for a mechanism beyond simple expansion. Flat geometry that prefers a balancing act. Ripples that carry the signatures of matter types, particle families, and cosmic speeds. The revelations accumulate with a softness that belies their power. The calmness of the field conceals a rigorous demand. Any hypothesis about early times must pass through this gate of precision. The background admits only those stories that reproduce its blackbody simplicity, its near isotropy, its delicate hierarchy of peaks, its sparse distortions. The shock is not only what the glow reveals, but what it refuses to permit. In that refusal, theories are shaped and pruned. A tranquil lantern becomes a stern teacher, and the lesson is consistency at a level that feels almost implausible for a sky so large and a history so long. The curve rises like a warm hill and falls with the poise of a sigh. That is the shape of a blackbody spectrum, a map of how much energy arrives at each frequency when matter and radiation have agreed to share heat perfectly. The curve is not accidental. It is the most democratic distribution nature permits, when equilibrium has settled every argument. For the background glow that fills the sky, this curve is not a guess. It is a measured promise, a calm signature of a fire that once filled everything and then cooled with exquisite grace. To test that promise required an instrument that could compare the sky to an almost perfect reference and hear the faintest differences between them. A spectrometer flew above the meddling blanket of Earth's atmosphere and carried within it a blackbody calibrator that could be warmed and cooled with surgical control. Radiation from the heavens and radiation from the internal standard were directed into a device that recorded their difference as a function of frequency. In an ideal match, the difference vanishes at every point along the spectrum. A small residual would mean that the sky diverged from the blackbody shape by some amount. The instrument's art was to make every source of internal error smaller than the cosmic whisper it sought. The result was stark in its serenity. Across a wide band of microwave and far infrared frequencies, the sky matched a blackbody with a precision that felt almost theatrical in its perfection. No bumps revealed late injections of energy. No hollows suggested missing light. The curve rose and fell like the textbook drawing. Only now the drawing was replaced by numbers, and those numbers converged on a single temperature. The mean value landed at about 725 Kelvin, with errors so small that the uncertainty became a footnote rather than a headline. It was as if the universe had been placed in a laboratory oven long ago and allowed to settle into the most even warmth possible, then released to cool without further mishap. Such a spectrum carries information that is not obvious at first glance. The total energy density of the radiation can be computed from the area under the curve. The number density of photons follows from the same physics. The universe contains hundreds of photons in every cubic centimeter, a bath so ample that each proton and electron swims in a sea of light. The ratio of photons to baryons emerges at around 1 billion to 1. That number encodes an asymmetry so deep in cosmic history that it reads like a foundational choice. With so many photons for every particle of ordinary matter, the radiation field dominated the dynamics of the young plasma, smoothing and pressing while gravity gathered its patience. The curve also sets a metronome for time. As the cosmos expands, wavelengths stretch, and the temperature drops in proportion to that stretching. The measured temperature today becomes a boundary condition that runs backward along the equations to infer earlier epochs. At a few thousand Kelvin, neutral atoms formed and the fog lifted. At millions and billions of Kelvin, nuclear reactions knitted the light elements. The spectrum does not recount those events in words. It sets the scale that makes those reconstructions consistent. When models of early times are run against it, their trajectories must land squarely on the gentle peak in the microwave band that instruments have drawn. The success of the black-body fit has a harder lesson hidden within it. To reach such purity, the early universe had to be very good at erasing imperfections in the radiation field. Compton scattering traded energy between electrons and photons. Double Compton processes and Bremsstrahlung created and absorbed low-frequency photons that filled in any gaps. These interactions require a dense, hot medium and enough time for many encounters. The spectrum's perfection says that those conditions were present and effective. If a late burst of energy had heated the plasma after equilibrium had essentially frozen, the curve would have been bent into new shapes. Tiny chemical potentials would have appeared at higher frequencies, or Y-type distortions at lower ones. Careful inspection found none of consequence, which implies that later fireworks in the universe's history did not spoil the relic light in a detectable way. The dipole pattern caused by motion introduced a graceful check. The spectrum appears slightly warmer in the direction of the solar system's travel, and slightly cooler behind. When that motion is subtracted, the monopole spectrum remains. Instruments independent of one another found the same temperature for this monopole, reinforcing the sense that the blackbody description was not an artifact of a single method or a single machine. The studies built a simple portrait with strong bones. There is a global temperature that defines the sky. There is a tiny velocity-induced tilt that can be removed. What is left is a pure curve that could hang in a gallery of physical laws. Beyond the curve's elegance lies its strategic value. A precise spectrum turns the background into a ruler. The heights and positions of any features layered atop it, however small, can be interpreted as signatures of physical processes that left their faint trace without violating the overall equilibrium. Once the baseline was established with such care, attention could shift to departures from uniformity on the sky. Tiny differences in temperature from one patch to another subtend angles that speak of pressure waves, gravity, and composition. The spectral baseline gave confidence that those angular variations were not artifacts of frequency-dependent distortions, but genuine imprints of conditions when matter and light were still tightly coupled. The lack of spectral distortions also anchored studies of the universe's later thermal history. Massive populations of early black holes or exotic decays of particles could have pumped energy into the radiation field. Galaxy clusters produce local Y distortions through inverse Compton scattering of photons off hot electrons. Those cluster signatures can be mapped because the global spectrum stays true. The sky becomes a mosaic where common tiles match the blackbody while specific tiles betray heating along particular lines of sight. The remarkable global purity makes the local exceptions more legible. The temperature itself has a quiet consequence on chemistry. Reaction rates for molecules in interstellar clouds and the spin states of atoms feel the presence of the background. A sea of photons at this temperature sets a floor beneath which certain transitions cannot cool. In laboratories and telescopes, this floor becomes a reference that must be included in models. Even in the calm life of a cold cloud where stars are not yet born, the ancient glow participates, an ambient light that never turns off. Detectors improved in sensitivity and control, and they confirmed the same melody. New instruments measured the spectrum across wider ranges, seeking any hint of subtle departures that earlier devices might have missed. The line held. Every successful replication deepened the central conclusion. The universe, as seen at these wavelengths, behaves like a single temperature radiator with astonishing fidelity. In an era when many measurements grapple with messy environments and uncertain calibrations, it is rare to find a cosmic quantity so obliging, so ready to be described by a closed form that fits everywhere it is tried. The promise embedded in the spectrum is philosophical as well as physical. It suggests that complexity can emerge from a beginning that knew how to relax. A furnace that once raged managed to distribute energy so evenly that, when released, its remnant cooled as one body. That unity left room for small differences to carry meaning. The curve became the canvas on which the subtle variations of later analyses could be painted. Without the canvas, the variations would be noise. With the canvas, they are information. The most relaxing fact of all may be this. A single number and a single curve can summarize the mood of the cosmos at a turning point when light decoupled from matter. The number is a temperature barely above absolute zero. The curve is a black body that rises and falls with unhurried certainty. From these, a lineage of inferences flows. Energy densities, photon counts, epochs of transparency, the efficiency of smoothing interactions, the absence of late disruptions, the clarity of later imprints. The universe revealed a clean profile of its own heat and then held still enough for careful listeners to confirm it. Across the sky, a pattern appears that is almost not a pattern at all, mottled by temperature freckles too small for ordinary senses to register. Instruments trace them in microkelvin, painting a globe of subtle highs and lows that resemble the faint grain of paper rather than the bold strokes of a mural. These tiny ripples are the quiet birthplace of structure. Within them hide preferences for where matter will gather, where gravity will amplify a whisper into a city of stars, where emptiness will widen into plains of near nothing. The calmness of their amplitude belies the audacity of their consequences. In the young plasma, photons and baryons moved together like a single fluid. Photons supplied pressure, pushing outward whenever matter tried to clump. Gravity pulled inward, inviting collapse wherever density ran a little high. The result was oscillation, an ancient ringing set by the speed of sound in the hot medium. Some regions were caught at crests, their pressure swollen and bright. Others were at troughs, their pressure slack and cool. The period of this rhythm depended on a simple ruler, the distance a sound wave could travel before light slipped free and the symphony of scattering ended. That ruler, the sound horizon, now appears as a preferred angular scale on the sky, a gentle signature written as if with a very fine brush. Photons remembered those oscillations as they decoupled and streamed onward. The memory arrived as temperature variations across the sphere, recorded by radiometers that scanned and rescanned, reducing noise by repetition and patience. The brightest spots are slightly hotter, the darkest slightly cooler, the difference so slight that it seems a contradiction to call them seeds. Yet these are the marks gravity required. After the plasma cooled into neutral gas, the pressure of light no longer fought as fiercely. Where the map shows slight excess, gravity found leverage. Over millions, then billions of years, the excess became filaments and knots. What began as a microkelvin nudge ended as a supercluster. The pattern bears more detail than a mere scatter of dots. It carries a hierarchy of harmonics, a set of peaks and valleys when studied as a function of angular scale. The first peak, near a degree, corresponds to regions that completed a half oscillation by the time photons decoupled, reaching maximal compression. The next peaks belong to regions that managed a full oscillation or more, arriving at rarefaction or the next compression just as the fog lifted. The relative heights of these peaks reveal the balance between radiation pressure and gravity, the amount of ordinary matter that adds inertia to the fluid, and the role of components that feel gravity without feeling light. A band-limited pattern becomes a ledger of the contents of existence. Not every scale survives intact. On the smallest angles, diffusion erased contrast. Photons wandered from hot to cold regions during the last 1,000 years of scattering, blending differences like cream swirled into tea. This effect, called damping, acts as a graceful fade in the power spectrum, rather than a sharp cutoff. The thickness of the last scattering surface and the frequency of scattering events set its strength. The map thus encodes not only where waves stood, but also how the final moments of interaction softened their edges. The gravitational potential wells that shaped photon energies left additional fingerprints. Photons climbing out of deeper wells suffer tiny energy losses and arrive cooler. Photons falling into shallower wells arrive slightly hotter. On the largest scales, where waves could not complete even a single oscillation, this imprint dominates. Gravity shifts the color just enough to be noticed by careful instruments. A subtle red or blue that says more about potential landscapes than about pressure music. As the universe later accelerated under the influence of a smooth energy component, those potential wells changed in time, adding a late bonus to the pattern along lines of sight that cross vast underdensities and overdensities. The whole sky becomes a palimpsest, early marks overlain by even later edits. Mapping the ripples required an acknowledgement of Earth and its inconveniences. The planet rotates, the atmosphere glows, the ground radiates, and the instrument itself warms. The solution was to choreograph scanning strategies that revisit each pixel from many directions, to couple each measurement to a known reference, to subtract a carefully measured dipole from local motion, and to keep frequencies diversified so that foregrounds could be identified and peeled away. The residual, after this ritual of removal, is improbably quiet. That quiet is the canvas for the microkelvin freckles, and on that canvas, the power spectrum emerges with the calm certainty of a heartbeat on a clinical screen. Once the map is established, the path from ripples to structure is not guessed, but computed. Gravity focuses matter into the slightly overdense regions, while cosmic expansion moderates the rate of that gathering. Dark matter participates first and most decisively, because it ignores radiation pressure. Ordinary gas follows, cooling, fragmenting, forming stars that ignite and enrich the medium with heavier elements. The final arrangement of galaxies, sheets, and voids is a grown version of the infant pattern. Statistical comparisons between the sky of ripples and the three-dimensional distribution of galaxies confirm this family resemblance. The same preferred scale that set the first acoustic crest becomes a standard ruler for later times, a distance encoded in the spacing of galaxies that helps measure the expansion with quiet accuracy. Polarization deepens the narrative. Thomson's scattering of anisotropic radiation produces a net polarization pattern with two distinct morphologies. One pattern arranges as radial or tangential fans, called E-modes, directly linked to the same acoustic oscillations responsible for temperature variations. The other pattern curls with a handedness called B-modes, demanding sources beyond density waves. Polarization thus offers a cross-check for the origin of the ripples and a sensitive test for phenomena like gravitational waves in the earliest moments. Even when the second pattern hides beneath the noise, the first arrives with clarity that confirms the acoustic story. The ripples also serve as a boundary on imaginative physics. Any exotic event that would have injected energy or altered the scattering history must leave traces in the power spectrum or in the statistics of hot and cold regions. The absence of strong non-Gaussian features, The near Gaussianity of temperature fluctuations constrains models that would have introduced skewness or unusual clumping at decoupling. The map is not only a picture, it is a courtroom, and many defendants fail to pass its standards. Foregrounds deserve a moment of calm respect. Dust in the home galaxy glows with a temperature of its own. Charged particles spiral in magnetic fields and radiate. Free electrons scatter and distort. Each of these processes has a spectral fingerprint, a way of rising or falling with frequency that differs from the relic pattern. By observing the sky in multiple bands, the contaminants can be separated like instruments in an orchestra, picked out by ear. The remaining map of ancient ripples is not contaminated silence. It is curated quiet, made trustworthy by the act of careful separation. There is a gentle humility in recognizing how little was required to start everything. A part in 100,000 is not dramatic, yet that is the scale of the initial preference that set gravity to work. If the ripples had been much smaller, structure formation would have been slow and sparse. If they had been much larger, the universe would have rushed into disorder, collapsing too quickly for stable, long-lived stars to spread metals and light. The observed amplitude sits in a generous middle that permits time for complexity to emerge without erasing the calm background that preserves memory. The artistry of the map answers a psychological need as well as a scientific one. It shows that the grandest outcomes can spring from patient modulations, that a universe does not require noisy beginnings to achieve cinematic landscapes. The freckles are enough. They are a lullaby that teaches gravity its melody and matter its dance. In their presence, the empty sky becomes full of possibility, not through sudden upheaval, but through cumulative, unhurried growth. The deepest relaxation emerges when the mind accepts the paradox. A field defined by near uniformity contains the instructions for all the later asymmetry. A surface that looks almost featureless to the impatient gaze carries the blueprint for the most elaborate structures. Quiet ripples, placed at the right time in the right medium, do not vanish. They recruit the whole of time to amplify them. The result is everything that can be named when one looks up at night, all of it traced back to a pattern on a sphere, measured in microkelvin, drawn in patience. Eyes were lifted above weather and city light, placed in quiet orbits where the sky could be seen whole. The first of these eyes rode a cold platform that drifted around Earth with unromantic purpose and exquisite restraint. It carried radiometers that measured differences between pairs of directions, rather than absolute brightness. That design let much of the instrument's own temper cancel itself out. It also allowed a slow painting of the sphere without preference. Strip by strip, spin by spin, the instrument traced a fabric of measurements that would later be stitched into the first full portrait of the ancient glow. Pixels were arranged with a scheme that favoured equal areas, so no region would be given privilege, and the result could be averaged and compared without bias. The map that emerged spoke softly, yet it covered the entire sky. Instruments need a reference to keep faith with reality. A natural standard was written across the heavens in the form of the dipole pattern, created by the motion of the observer through the background. That pattern is simple in shape and large in amplitude compared to the tiny ripples, so it became a calibrating lantern. Each sweep across the dipole provided a precise yardstick for gain and pointing. Where the pattern brightened against the motion, the numbers rose. Where it dimmed behind, the numbers fell. The cycle repeated with every pass. Over months, the calibration settled into a confidence that could support refinements down to microkelvin scales. The first portrait carried two gifts. It confirmed the uniform temperature with a precision that pleased mathematicians. It also showed that fluctuations truly existed, mottling the calm at a level just right to seed structure. The view was coarse by modern standards, yet it was a revolution in mood. The sky that had seemed featureless revealed itself as a gentle relief map that invited deeper surveys. The features were not random scratches. They were statistically well-defined, nearly Gaussian in distribution, and precisely measured over large angles where cosmic randomness was once suspected to smear everything into ambiguity. A second-generation eye took the lesson to heart and concentrated on clarity. It rode a path around the second Lagrange point, a location that provides stable thermal conditions and an uninterrupted view of space. There it spun like a patient ballerina, scanning great circles that slowly precessed to cover every coordinate on the sphere. The hardware used high-electron mobility transistor amplifiers, cooled to reduce their own hum. The detectors listened in multiple microwave bands, each chosen to separate cosmic signal from galactic clutter. The strategy was differential again, comparing pairs of sky directions to cancel drifts and common modes. The data fell to Earth in a steady stream that looked like a tangled ribbon at first glance, then like a woven tapestry as algorithms arranged it into maps. Foregrounds threatened to muddy the picture. The home galaxy contributed synchrotron radiation from charged particles moving in magnetic fields, free emission from electrons floating past ions, and thermal radiation from dust warmed by starlight. Each of these rose and fell with frequency in a distinct way. By observing the sky at several bands, the foregrounds could be modelled and subtracted with tools that blended statistics with astrophysical understanding. Some methods assembled a clean map by combining frequencies in a way that minimized variance while preserving the expected spectrum of the background. Other methods built component models pixel by pixel, solving for the mixture of emissions that best matched the data while imposing smoothness and physical plausibility. Masks were applied to the brightest parts of the galaxy and to known point sources so that the underlying field could be studied without contamination. What remained after this care was a map of the ancient afterglow that balanced reach with reliability. The map was not only an image, it was a set of numbers that could be folded into a power spectrum, a summary of how much variance lives at each angular scale. The instrument's beam softened features by a known kernel, and that effect was carefully deconvolved. Noise varied across the sky depending on how often each pixel had been visited, and that variation was tracked through weight maps. Likelihood functions were constructed to compare models with data while honestly accounting for cosmic variance at large scales and instrumental uncertainty at small scales. Curves that theorists had drawn were placed atop points with error bars, and the match revealed a good fit that carried meaning for parameters of interest. Baryon density, dark matter density, the overall curvature, the tilt of the primordial spectrum, each found a home in numbers with quoted uncertainties and correlations. A third eye arrived with finer resolution and colder hearts in its detectors. It also waited at the second Lagrange point, shielded from the warmth and radio noise of Earth by distance and design. Bolometers, cooled to fractions of a degree above absolute zero, registered heat from incoming photons as tiny changes in resistance. Arrays of these sensors watched the sky in bands spread from the microwave into the submillimeter, revealing both the background and the drapery of dust with exceptional clarity. The scanning strategy again favored great circles and repeated visits, building redundancy that could expose subtle systematics. Side lobes were measured and modeled. Pointing was tracked to arc-minute precision, and the time-ordered data were filtered to remove thermal drifts without distorting the sky's genuine signal. A complete portrait emerged that set a new standard for detail. Temperature maps showed sharp acoustic features in the power spectrum to high multipoles, revealing the damping tail with elegance. Polarization maps added another layer of truth, showing the expected E-mode patterns that align with the story of pressure waves and scattering. The combination of temperature and polarization tightened constraints on the ionization history of the universe and on the total mass of neutrinos. Lensing of the background by intervening large-scale structure was reconstructed by tracing the tiny distortions it imprints on the otherwise random field. That lensing map traced the web of matter, both luminous and dark, and allowed cross-checks with galaxy surveys and with the imprint of galaxy clusters. Data became more than the sum of images when combined with other cosmic measurements. The preferred acoustic scale seen on the sky also appeared as a standard ruler in the spacing of galaxies. The late-time brightening of cold spots along lines of sight that pass through large underdensities a subtle effect of a changing expansion rate, emerged in cross-correlations between the background and maps of galaxies. The harmony between independent methods strengthened confidence in basic narratives while leaving room for puzzles that invite careful scrutiny. Calibrated subtlety replaced crude agreement. Behind every map lay teams that watched for mischief in the numbers, thermal fluctuations in the spacecraft, microphonic noise, cosmic rays striking detectors, sidelobe pickup from the Sun, Earth, and Moon when the geometry allowed. Each had a signature that could masquerade as sky if left uncorrected. The cure was redundancy and transparency. Multiple detectors at the same frequency. Multiple observing seasons. Simulations that injected known problems and tested the analysis chain. Null tests that should return only noise if the pipeline behaved. When a failure appeared, the systems were tuned or the data were flagged. Confidence grew not from blind faith, but from 1,000 small proofs. The full sky images of temperature and polarization, projected in soft mole-wide form, became modern icons. They were not paintings in the sentimental sense, yet they carried aesthetic weight. The gentle splashes of cool and warm, the delicate curl patterns in polarization overlays, the masked band of the Milky Way politely absent in certain versions. Viewers could admire them without knowing their content. Readers of the numbers behind them could translate those colors into parameters with tight error bars. Both responses were justified, one emotional and the other formal. A quieter achievement lived in the public release of the maps and the tools used to analyze them. The data were placed where anyone could test hypotheses, run alternative pipelines, and generate their own summaries. Independent groups reproduced the main results, sometimes with fresh approaches to component separation or to foreground modeling. Success across teams reduced the chance that a hidden assumption was steering conclusions. Confidence deepened with each replication, and the field learned to expect that any claim would be met with healthy verification. The sky is not a single channel of information. It is a network that includes temperature, E-mode polarization, and the subtle lensing deflections that connect distant past to nearer structure. Instruments in orbit captured that network with patience and care. They offered not a single revelation that changed the world overnight, but a sustained view that changed the tone of inquiry. Cosmology moved from impression into measurement, from debate into precision. The eyes in space did not shout. They observed, shared, and refined, until the map of the ancient afterglow stood as calmly as a globe on a desk, ready to be turned and studied from any angle. A thought arrives with the softness of first snow. Suppose the early universe took a deep breath and grew at a pace so steady and so fast that every wrinkle was ironed and every corner was pulled beyond sight. Suppose space expanded not by inches, but by factors, doubling again and again until what was once near became unimaginably far. This is the idea of inflation, a period when the scale of the cosmos climbed like a smooth exponential curve, quieting chaos and laying a calm foundation for everything that followed. The mechanism is written in the language of fields. Imagine a field that fills space the way air fills a room, carrying energy even where no particles dance. If that field sat high on a gentle slope of potential energy and rolled downward very slowly, its nearly constant energy density would act like an engine for accelerated expansion. Gravity, usually a gatherer, becomes a pusher when energy is stored in this special form. The result is repulsive on the largest scales, a pressure that makes distance grow faster than light can cross it. No law is broken because nothing moves through space at that speed. Space itself changes its scale. Two conditions make the process tranquil. The first is friction from the expansion itself, often called Hubble friction, which keeps the field from racing down its hill. The second is the shape of the potential, which must be flat enough to delay the fall. When both hold, the field evolves slowly and the expansion stays smooth. Physicists translate this picture into small parameters that measure the laziness of the roll. When those parameters remain tiny for long enough, the stage is set for a vast swelling that stretches space by dozens of E-folds. each fold a multiplication that quickly turns small regions into enormous ones. The virtues of such a swelling are practical and serene. Regions that once shared heat and information are blown far apart, which explains why the sky looks nearly the same in directions that cannot communicate today. Uniformity is not a coincidence. It is a memory of a time when the world was closely knit before expansion carried pieces out of conversation. Curvature is also tamed. Any initial bend in space is diluted as distances grow. A sphere, or a saddle, is pressed toward flatness, until straight lines remain straight to a remarkable degree. Exotic relics that might have cluttered the early universe, heavy defects in the fabric of fields, are diluted beyond detection. The swollen stage is clean and ready. Inflation does not simply smooth, it also seeds. Quantum mechanics refuses to be silent, even when a field rolls gently. Tiny fluctuations arise uninvited, jittering the value of the field in one place relative to another. During accelerated expansion, those jitters are stretched until their wavelengths exceed the horizon size. Once larger than the horizon, they can no longer oscillate like ordinary waves, and their amplitudes freeze into place. The process turns microscopic uncertainty into macroscopic structure. When inflation ends and ordinary expansion resumes, the frozen ripples re-enter the horizon and begin to evolve under gravity and pressure. The map of slight over and under densities is born from the faintest tremors of the vacuum. This mechanism carries a predictive fingerprint. The spectrum of the initial ripples is close to scale invariant, meaning that no particular size is strongly preferred. Larger and smaller waves have similar power, with a gentle tilt that reflects the slope of the rolling field. The ripples are nearly Gaussian, a statistical way of saying that their heights and depths follow a simple bell curve without strong skewness or spikes. They are adiabatic in character, which means that all components of the young mixture rise and fall together rather than slipping out of step. These traits are not decoration. They are the natural outcome of a single, slowly rolling field that sources the perturbations. The coherent phases of those ripples matter. Because they were frozen while outside the horizon, then released in unison as expansion brought them back inside, they began their acoustic motion with the same clock setting. This coherence later reveals itself as a series of peaks in the pattern of temperature variations and as a familiar scale in the arrangement of galaxies. Without the synchronization that inflation provides, the peaks would be smeared or misplaced. The calm rhythm seen in the sky becomes a drumbeat that points back to frozen waves thawed in concert. Inflation must end, or else no stars or atoms would form. The field completes its role, or it reaches a place where the gentle slope gives way to a steeper descent, and the engine of accelerated growth shuts off. Energy stored in the field is then converted into a hot soup of particles in a process called reheating. The comfortable phrase hides a turbulent moment when fields decay, quanta are produced, and temperatures climb to values beyond any ordinary furnace. From that heat, the familiar story of a cooling plasma begins. The start is hot and dense, yet it arises from an expansion that was cold in its temperament. A quiet swell hands the baton to a lively fire. The shapes of possible potentials invite imagination. Some are simple monomiles, others flatten into plateaus that prolong the slow roll. Some descend gently then steepen, which can leave slight features in the pattern of ripples. Each shape implies a different tilt of the spectrum and a different weight of long versus short waves. Measurements of the cosmic pattern act like surveyors, comparing these shapes to the realized sky. A path that yields the right degree of smoothness, the right number of E-folds, and the right statistical character of the ripples earns more attention. A path that misses those marks is set aside. There is also the question of gravitational waves born from the same swelling. Accelerated expansion would amplify quantum fluctuations of spacetime itself, producing a background of primordial ripples that leave a faint curl pattern in the polarization of the ancient light. The amplitude of that pattern is tied to the energy scale of the swelling. A strong signal would point to a high plateau on the potential. A weak or absent signal would favor lower plateaus or more complicated dynamics. The search for this curl is therefore a search for the height of the first stage on which the cosmic drama played. The mathematics of inflation paints a portrait of relaxation with discipline. Exponential growth sounds extravagant, yet it is the most efficient way to forget initial conditions and to bring a system to uniformity. Small local differences are stretched beyond relevance. Curvature is ironed to near zero. The clock is reset so that regions begin their later evolution in harmonized rhythm. The picture is not an empty promise. It contains a clear algorithm for producing the statistics of the ripples that later become galaxies. It offers a reason for why the sky looks smooth without being bland, structured without being chaotic. Skepticism has space here and does not break the calm. Any model of the earliest times must shoulder the burden of initial settings. Why was the field high on its slope? Why was the potential gentle enough for slow roll? These are legitimate questions. Some propose that a wide variety of starting conditions eventually find themselves on gentle slopes because only those regions inflate and become large. Others look for deeper principles that select certain potentials through symmetry or quantum gravity effects. None of this restlessness erases the clarity of the footprints that an inflationary stage would leave, footprints that can be checked against the calm map of the ancient light. The most relaxing feature of this idea may be its economy. A single ingredient, a field with a suitable potential, performs several tasks at once. It explains uniformity across unreachable distances. It sets the geometry near flat. It supplies the seeds of structure with the right statistical character. It predicts signals that can be sought in temperature patterns, polarization curls, and the spacing of galaxies. It does all this without complicated choreography, relying instead on the natural behavior of fields and the simple effect of energy density on the expansion of space. Even the end of inflation has a soothing logic. As the field finishes its work, it hands the universe a hot beginning that carries no memory of prior disorder. The tumult happens at the transition, not in the growth itself. From there, the cooling proceeds with rules that are well understood, leaving room for stars to form and for life to notice the quiet evidence left behind. The breathing of space in that first deep inhale remains invisible to the eye, yet its consequences are visible everywhere the eye looks. A period of swift, steady growth, a field rolling lazily, quantum jitters stretched into the blueprint of the night. The picture is at once audacious and calm. It is not asserted as doctrine. It is offered as a way to make sense of a sky that looks too coordinated to be accidental and too subtly patterned to be artless. If the early universe did swell in this gentle manner, then the present calm of the ancient glow is not a coincidence. It is the memory of that first breath, preserved in light. In the hot young plasma, a rhythm travelled outward like a tide, a pressure wave riding on light. Photons lent stiffness, baryons lent weight, gravity tugged, and the result was a pulse that moved through the medium with a well-defined speed. The speed was set by the balance of radiation pressure against inertia, roughly a familiar fraction of light's own pace. From each small overdensity at the center, a spherical crest expanded. Around that crest, the fluid was slightly denser and slightly hotter than its surroundings. It was not a loud wave. It was a steady heartbeat that repeated across the entire early cosmos, each source sending a shell of compression outward. As the plasma cooled, electrons settled into orbits and let neutral atoms form. Photons no longer scattered every moment. Light began its long journey through space. Baryons, freed from the insistence of radiation, found themselves caught between two invites. Inside the original overdensity gravity urged infall. At the radius that the wave had reached by the time scattering ended, matter was piled into a ring of mild excess. The process did not create a sharp wall. It left a preference for one particular separation between pairs of points in the matter field. That separation is the distance the wavefront travelled before light decoupled. It is called a sound horizon, and it became a ruler set into the architecture of space. The ruler survives even as the universe matures into a web of filaments and nodes. Gravity pulls matter back toward centers. Motions on many scales blur patterns, yet a faint statistical memory persists. The chance of finding two galaxies separated by the sound horizon is slightly higher than the chance of finding them at nearby distances. The signal is not obvious to the eye when looking at a single photograph of the sky. It appears when one counts patiently, when one builds a correlation function and asks at what separations pairs are more common. There, a soft bump rises at the preferred scale. It is not a trumpet call. It is a steady drumbeat, hidden in the numbers. The physics behind the heartbeat is forgiving and clean. The speed of the early sound is determined by simple ratios of radiation and matter. The time available for the wave to travel is set by the cooling schedule that leads to transparency. The distance the crest reaches depends on these two ingredients alone. Details of complex astrophysics that arrive later cannot change the basic ruler. They can smear it, but they cannot move it far. That resilience is a gift. It means the ruler can be used to measure the size of the universe at many stages, because the co-moving length of the sound horizon is preserved while the apparent size in the sky changes with expansion. Observers collect redshifts and positions for millions of galaxies, then fold that catalogue into a three-dimensional map. Within this map, the ruler appears in two directions at once. Along the line of sight, the spacing in redshift is connected to the expansion rate at the time those galaxies emitted their light. Across the line of sight, the angular separation is connected to the cosmic distance to that epoch. By comparing the measured bump to the known co-moving ruler, the expansion history can be traced without leaning on fragile candles. The method is geometric and calm. It answers with a simple relation between scale and angle, scale and redshift, and these relations tie directly to the rate at which the universe has been stretching. Nonlinear growth tries to blur the ruler by stirring matter on smaller scales. Random motions in clusters smear separations along the line of sight, while the gentle tug of gravity broadens features in the correlation function. Analysts respond with a technique called reconstruction. They estimate the large-scale flow that has dragged galaxies from their original positions, then shift galaxies backward along that inferred flow. The procedure sharpens the bump as if refocusing a scene that had drifted slightly out of alignment. The sharpened ruler then yields distances with improved precision. The gain is not theatrical. It is measured in a quiet narrowing of error bars, in a steadier curve for the cosmic scale factor. The heartbeat is not confined to bright galaxies. It appears in the forest of absorption features etched by diffuse gas, where light from distant quasars passes through filaments and records the imprints of small variations in density. It can be traced in the way galaxies drift relative to each other thanks to peculiar velocities that add to Hubble flow, though that signal requires care to separate from the preferred scale. Future instruments aim to map neutral hydrogen over gigantic volumes, using the 21 centimeter line, treating the sky as a field of intensity rather than a census of individual objects. In each case, the same ruler offers itself. A single scale imprinted in the plasma becomes a tool that travels across many tracers. The ruler carries cosmological content. Its length depends on the densities of ordinary matter and radiation when the wave was traveling. Those densities cannot be chosen arbitrarily. They are linked to other measures of the ancient light, and the harmony between them reduces ambiguity. When combined with the map of temperature ripples and polarization patterns, the heartbeat adds leverage on parameters that describe the current acceleration. It helps constrain how the expansion rate changes with time. It adds a graceful check on whether space keeps the same geometry as distance grows. It reports on the possibility of subtle changes in the physics of the early plasma, such as additional light species that would speed its clock. Foregrounds add gentle complications that can be untangled with patience. Galaxy surveys must correct for selection effects, dust obscuration, and the way the brightness of galaxies affects the chance they are included. Redshift measurements come with uncertainties that spread positions along the line of sight. These issues wash over the preferred scale but do not rewrite it. Statistical techniques correct the leading biases. Simulations test the corrections by building mock universes where the true answer is known. The measured ruler is then compared to the true ruler to reveal any systematic offset. Through this slow feedback loop, the measurement becomes trustworthy. The presence of the ruler in both the ancient light and the later web provides a bridge. The scale, as measured at a given redshift, can be translated into a statement about cosmic distances and the expansion rate at that time. Drawing a curve through these statements from one redshift to another outlines the history of the scale factor. The curve does not need constant hand-holding from stellar models or assumptions about the brightness of standard candles. It follows from geometry and from the memory of a wave that once rolled through a hot sea. The story is compact. A pressure wave left a mark. That mark, read with care, reveals how the stage has grown. The heartbeat invites philosophical quiet too. A universe that began with violence still chose to keep time with a gentle metronome. It did not select a ruler carved by coincidence. It built one from the basic behavior of a fluid under gravity and light. The ruler asks for no grand machinery to be useful. It asks only for a count of how often galaxies come in pairs at a particular separation. That simplicity offers reassurance. Even when details multiply and surveys grow to fill continents with glass and electronics, the core insight remains modest. A wave travelled a distance. That distance lingers. The lingering distance becomes a measure of everything beyond it. If a sketch were drawn, it would show spheres expanding from tiny seeds, then freezing when the fog lifted, then collapsing inward while a ring of preference remained. That ring became a subtext in the grand pattern of matter. It is still there, almost shy. Its strength is not in spectacle. Its strength is in being anchored to early, calm physics that many independent observations confirm. With each new survey, the drumbeat grows clearer, not because it grows louder, but because ears have learned where to listen. The heartbeat is a lesson in patience. Waves needed hundreds of thousands of years to travel to their appointed radius. Galaxies needed billions of years to grow into tracers that make the ruler legible. Human teams needed decades to design instruments, gather measurements, and refine methods. The payoff is a ruler set by nature that can be carried across time. With it, the pace of expansion can be tested, the shape of space can be checked, and the quiet energy that speeds the present era can be weighed. A soft crest that once moved through a bright fog now guides the hand that draws the curve of the universe. Light remembers how it was last scattered. When free electrons in a thinning cosmic fog met radiation that was slightly brighter in some directions and dimmer in others, they imprinted a pattern in the outgoing waves. The rule is simple and elegant. Thomson scattering produces linear polarization only when the incoming light carries a quadrupole, a cloverleaf of brightness on the sky around each electron. From that geometry, a preferred orientation emerges. Across the heavens, those orientations knit together into a field that can be read like script. Two letters dominate the alphabet. One resembles gradients and ripples that flow without curl and is called E. The other curls like eddies on water and is called B. Together they form a quiet code in the afterglow. This code is not drawn with ink but with angles. At every point on the sphere, a tiny stick could be drawn to show the direction of polarization and a small number to show its strength. The sticks do not point randomly. They align and splay in patterns dictated by the density waves and gravitational potentials at the time of last scattering. Mathematically, the patterns can be decomposed with tools that respect the spin nature of polarization, a tidy bookkeeping that separates the curl-free E component from the divergence-free B component. The separation is not a matter of taste, it is enforced by symmetry. Density fluctuations, which compress and rarefy the plasma without twisting space, generate only E to first order. Gravitational waves, ripples in space-time itself, are free to write both letters. E emerges as the common script. Its power spectrum rises and falls in step with the acoustic music of the plasma. Peaks in temperature fluctuations have partners in polarization, and the crosstalk between the two encodes the timing of the oscillations. A striking feature hides in that crosstalk. At degree scales, temperature and polarization show an anti-correlation that betrays superhorizon coherence at the time of last scattering. Waves that had not yet completed a full cycle still left synchronized marks in two different channels. The pattern is calm and insistent, a signature that demands a mechanism that set the initial phases with care. B holds the promise of deeper history. If a background of primordial gravitational waves existed during the earliest moments, its stretching and squeezing of space would have induced a swirl in the polarization field at large angular scales. The resulting B would peak around a few degrees on the sky. Its amplitude is often expressed as a ratio R between tensor and scalar power. A large value would lift the curl into clear view and point to a high energy plateau for the earliest dynamics. A small value would leave the curl faint or absent, favoring gentler beginnings or more elaborate field behavior. The search for that curl become a search for the height of the first stage. Even without a primordial swirl, B does not vanish. As the ancient light travels through the growing cosmic web, its path is bent by gravity. Lensing by intervening structure remaps the polarization field and converts some E into B. The conversion is small but widespread, a fine fog of curl that concentrates on arc-minute scales. That fog is both a nuisance and a tool. It masks the larger scale primordial curl one hopes to see. It also carries a map of the matter between the last scattering surface and the observer. By measuring correlations between modes and applying quadratic estimators, one can reconstruct a deflection field that traces the distribution of mass. With that reconstruction in hand, the fog can be reduced through a process called delensing, sharpening the view of any underlying primordial B. Reionization introduced an encore for polarization at the larger scales. When the first luminous objects formed, they heated and ionized the surrounding hydrogen, releasing a new population of free electrons that could scatter the background light once more. That late scattering generated additional E-power on broad angular scales and a corresponding bump in the cross-correlation with temperature. The amplitude of this bump informs the optical depth to reionization, a measure of how opaque the universe became again before clearing once more. In this way, the polarization field records not only the last scattering, but also the dawn of the first structures. Experiments designed to read these letters favor patience and cold. Detectors are chilled to fractions of a degree to quiet their own thermal chatter. Arrays of polarimeters stare at chosen patches of sky for long seasons, rotating half-wave plates or modulating their beams to separate true polarization from instrumental quirks. The beams are measured against bright planets and carefully modeled to avoid false curls from small asymmetries. Scan strategies crisscross fields at multiple angles to average downstriping and to isolate systematics that follow the ground or the instrument rather than the stars. Each step is an act of deference to the minute amplitudes involved. Microkelvin signals do not forgive sloppy choreography. Foregrounds write their own letters and must be heard clearly to be removed. In the home galaxy, long chains of dust grains align with magnetic fields and emit polarized radiation that rises toward higher microwave frequencies. Charged particles spiraling in those fields produce polarized synchrotron emission that grows stronger at lower frequencies. Neither imitates the spectrum of the ancient blackbody perfectly. By observing in many bands, the two intruders can be modeled and subtracted. Spatial variation in their properties complicates the separation, but the problem yields to combinations of maps and to algorithms that adapt coefficients across the sky. Masks cover the brightest regions. Residuals are assessed by null tests that split the data by time, by detector set, and by scan direction. Only after these trials does the remaining curl earn the right to be taken seriously. The polarization field deepens the ledger of contents. E and its crosstalk with temperature tighten constraints on the baryon density, the slope of the primordial spectrum, and the expansion rate around the time of last scattering. Lensing derived from polarization refines the total mass of neutrinos, because those elusive particles delay the growth of structure and soften the deflection field. Even the combination of small b from lensing and large E speaks about spatial curvature with a quiet authority, complementing statements made by temperature alone. Every channel listens to the same epoch through a different sense. Delensing offers a reassuring path forward. Independent maps of structure from galaxies, quasars, or the faint glow of dusty star-forming galaxies act as guides. Cross-correlations between those traces and polarization maps reveal how much of the curl can be assigned to bending. Subtracting a predicted lensing B, derived from E, and the reconstructed deflection field reduces the fog. What remains is closer to the primordial canvas. The method has already sharpened constraints and promises more as detectors multiply and sky coverage grows. Systematic effects are hunted with an almost meditative routine. Polarization, angle calibration uses distant clouds, planets, or artificial sources lofted to high altitudes. Cross-polar response is measured in the lab and monitored on the sky. Bandpass mismatches can imprint false signals when foreground spectra vary across the beam. They are modeled and corrected. Ground pickup and side lobe contamination are suppressed by baffles and by scan strategies that keep the instrument at favorable orientations relative to Earth and Sunday. The virtue lies not only in building clean instruments, but in designing tests that force hidden errors into the open. A quiet reward for this effort is aesthetic. Polarization maps reveal filaments and swirls that trace the Milky Way's magnetic anatomy with painterly grace, even as they serve as obstacles to be removed. In the cleaned versions, the remaining E patterns flower into fans and rings that echo the acoustic heritage. When the curl is shown, it often looks like a delicate frost upon the window of the universe, thin and intricate. The beauty is incidental to the measurement, yet seems appropriate for a signal this old and this modest. The letters carry a philosophy of evidence. Temperature alone could have been a lucky coincidence, an accident of initial conditions that happened to match a simple model. Polarization multiplies the tests. It asks whether the same acoustic clocks that beat in temperature also beat in orientation. It asks whether gravity has quietly bent the path of light in ways consistent with the observed web of matter. It asks whether the earliest stretch of space left a curl that cannot be mimicked by density waves. Each answer lowers the pulse of doubt. In the end, the code reads calmly. E is abundant and harmonious, with a story of pressure and light. B is present at small scales due to lensing, and is being peeled back to expose whatever primordial curl may lie beneath. Reionization leaves a broad accent that times the first lights. Foregrounds are loud where the galaxy is busy, and are subdued where the sky is clean. Instruments are learning to whisper with the same restraint as the signal they seek. 1,000 small alignments make it possible to listen. When the letters are finally read without ambiguity, the earliest moments will not announce themselves with a shout. They will sign their name with a curl. A disagreement settles like a low hum beneath the music of the sky. It is not a crash of cymbals. It is a persistent undertone that refuses to blend fully with the rest. The hum is a dispute about tempo. How fast does the universe expand at this very moment? The question is posed with a single symbol that feels almost domestic in its simplicity. A rate per megaparsec, a speed per measure of distance, a metronome for space. The answer appears to depend on where one listens and on which clock is trusted. One path listens to the ancient glow and reads its pattern as a set of instructions. The ripples in temperature and polarization encode the contents of the early plasma and the geometry of the stage. From that encoding, a curve can be drawn forward that predicts how fast space should be stretching now. The curve is not guessed. It is the output of equations that turn densities into tempos. The result is a calm value with tight uncertainties, as if written by a steady hand. It arises from a view of the universe when it was young, then extended to the present with rules that have been tested in many ways. The other path declines to extrapolate. It builds a local ladder, rung by rung, from distances that can be measured directly to distances that cannot. Parallax establishes the first steps by watching nearby stars shift against background fields as Earth orbits the Sunday Cepheid variables with reliable brightness patterns extend the reach. Type Ia supernovae, with standardized luminosities after careful correction, carry the calibration far beyond any single galaxy. Each rung is cross-checked against anchors, such as masers, orbiting the heart of a spiral or the tip of the red giant branch in stellar populations. When the ladder reaches out to modest redshifts, the slope of recession velocities against distance gives a present expansion rate that can be read without ever consulting the ancient pattern. These two tempos drift apart. The early method prefers a slower pace. The local ladder prefers a quicker one. The difference is not a quibble within error bars. It is large enough to feel like a real tension rather than a misunderstanding. Instruments have been rebuilt and recalibrated. Catalogues have been sifted for biases that might tilt the ladder or smudge the ancient map. Teams have cross-examined their own assumptions with an almost ceremonial patience. The hum remains. The attraction of a tension like this lies in its ambiguity. One explanation would soothe the nerves. Hidden systematics could be gnawing at one of the pathways. Dust in host galaxies might bias the supernova light curves. The crowding of stars could shift the brightness of Cepheids in ways that are hard to model. Parallax 0 points might need fine corrections. On the other side, small mismatches in instrument beams or foreground models could lean on the inferred early parameters and propagate forward into a biased present rate. Every suspected culprit invites a gentle audit. Distance anchors are compared. Reddening laws are reconsidered. Alternative standard candles take a turn. The ancient map is reanalyzed with new pipelines and with new masks. The ceremony has become part of the rhythm. Another explanation invites new physics. A slightly different cast of light particles in the early plasma would change its clock, altering the distance to the sound horizon and hence the forward prediction for the expansion today. A gentle injection of energy before atoms formed could reshape the timeline that moves from a hot, opaque medium to a transparent sky. A change in how gravity behaves on large scales might lower or raise the present pace without disturbing the early fit. Dark energy with a whisper of evolution could keep the early universe in line while bending the late curve. These proposals are built with restraint. They try to preserve what works, while shifting a single hinge that could relax the tension. Independent witnesses are called to the stand. Time delays in strongly lensed quasars provide a geometric speedometer that depends on the mass distribution along the line of sight and on the expansion rate. The acoustic ruler in the spacing of galaxies, when combined with primordial abundances from nuclear afterglow, can be used to step down from early times without touching supernovae. The drift of galaxy ages against redshift offers a chronometer that is stubbornly simple in concept, but delicate in practice. None of these are perfect. Each has unique frailties, yet together they sketch a field of values that either cluster around one tempo or that leave room for the other. The shape of this field evolves as data accrue, and the hum grows either louder or softer depending on the day one listens. There is a quiet courage required to tolerate the tension. Precision invites pride, and pride resists contradiction. Yet the rhythm of science improves when a persistent discord forces methods to sharpen and models to loosen in just the right places. New instruments view Cepheids in crowded star fields with resolutions that separate neighbors cleanly. New surveys gather thousands of supernovae with uniform calibration, mindful of subtle population drifts. New maps of the ancient glow revisit polarization with deeper sensitivity and bring delensing to maturity, reducing the fog that blurs information. Each improvement is a movement toward clarity rather than a verdict. The language used to describe the dispute is careful. It is a difference between early inference and late measurement. It is a split between model-anchored prediction and distance ladder observation. It is not a failure of either approach. The early inference rests on a theory that has survived tests across a spectrum of phenomena. The late measurement rests on geometry and on standardized light that has been vetted in nearby laboratories of stars. Both deserve respect. The tension is a chance to check whether the bridge between them is missing a plank. There is a philosophical residue that clings to the numbers. The present expansion rate feels like a fact that space should simply confess. Instead, it reveals a personality, as if the universe were willing to speak fluently in two dialects at once. In one dialect, it recounts its youth and projects forward with austere logic. In the other, it offers a local testimony built from candles and rulers. The two dialects are not enemies. They are two ways of being consistent. If they converge, the relief will be deep. If they do not, the invitation to revise the script will be irresistible. Patience remains the dominant virtue. Rungs on the ladder are not repaired overnight. Anchors are not verified in a single observing run. Instruments that listen to the ancient glow require years of cooling and scanning to lower their noise to the level where a small shift in a parameter can be trusted. Surveys that measure the acoustic ruler must cover volumes so large that continents of glass and metal are assembled to collect the light. This slow architecture offers protection against sudden enthusiasm. It gives time for errors to announce themselves in patterns that cannot be reconciled with the rest of the network. If the hum resolves, the outcome will likely feel inevitable in hindsight. A corrected bias in a catalogue, a refined parallax zero point, a dust law that bends a subtle curve, a recalibrated beam shape, a small shift in the balance of early particles, a mild evolution in the dark energy script. Each candidate is modest in isolation. The result would be peace between two tempos and a single metronome for the present day. If the hum persists, the mystery will deepen not by growing louder but by continuing to refuse easy resolution. That refusal will be an honest guide toward either a hidden flaw or a quiet frontier of new physics. Until then, the numbers remain on the page, precise and slightly at odds, like two lines of music written in different keys that somehow share a melody. The contrast is instructive. It keeps attention focused, it prevents complacency, and it preserves the sense that even a well-mapped cosmos can surprise at the decimal place. A universe that carries its most ancient light with such calm may still keep a small secret in the pace of its expansion. The hum is not discord for its own sake. It is a reminder that measurement is a living art, and that truth often arrives as a slow alignment rather than a shout. Gravity can be felt without light. A hidden mass threads the cosmos like a patient riverbed, guiding currents that the eye cannot see. In the ancient plasma, it did not shine or scatter. It simply weighed, and that weight arranged the music of the early ways with a firm, quiet hand. The relic glow preserves evidence of this invisible presence in patterns that could not exist if ordinary matter were the only actor. The testimony is written in the heights of peaks, in the timing of oscillations, and in the steadiness of gravitational wells that cradled the photons as they began their long flight. The earliest effect is architectural. Before atoms formed, radiation and baryons were tightly coupled and behaved like a springy fluid. Dark matter did not join that dance. It flowed nearly freely, responding only to gravity, and grew perturbations earlier and more efficiently than the coupled plasma could manage. Those dark perturbations dug potential wells that were deeper and more stable than anything pressure-supported matter could build. Photons climbed into and out of those wells as they scattered, gaining and losing tiny amounts of energy. The exchange set the stage for a pattern in temperature that bore the imprint of two clocks at once. One clock belonged to acoustic oscillations, the other belonged to gravitational potentials set by dark matter. The ratio of odd to even acoustic peaks reveals the baryon loading of the fluid, but the overall scaffolding of the peaks depends on when matter began to dominate over radiation. That moment of equality determines how quickly potentials decay while waves are still moving. With abundant dark matter, equality arrives earlier, potentials persist longer, and the first crest gains strength from the early integrated influence of gravity. The first peak rises, the next peaks settle into a characteristic ladder, and the damping tail lands in a predictable slope. Without dark matter, the ladder would look wrong, the phases would shift, and the coherence that unites temperature and polarization would be compromised. The invisibility of this mass hides a virtue. Because it does not collide with light, it does not erase small structures in the plasma. Its free streaming length is tiny if it is cold, so it preserves contrast on scales that pressure would otherwise smear. That preservation leaves a crispness in the pattern at small angular scales, a crispness that would blur if the unseen mass were warm and moved at appreciable speeds in the early epochs. Limits on how warm it could be follow from the very existence of fine structure in the temperature map and in the E-mode polarization. Too much particle velocity would have softened the pattern beyond what the data allow. Gravity never stops at boundaries. After photons decoupled, the dark matter continued to shepherd growth. Lensing by the web that formed later subtly distorts the ancient field. The deflections correlate distant modes and turn some E-mode polarization into B-mode curls. From these faint correlations, a map of mass emerges that does not care whether that mass glows. The consistency between this reconstructed web and the statistical needs of the acoustic peaks forms a circle of confirmation. The same invisible component that shaped early wells later bends the light that escaped those wells. Two eras, one actor, joined in evidence by the way, straight paths are gently curved. Abundance is the next quiet clue. The total density of ordinary matter can be read from the alternation of peak heights. Baryons weigh down compressions more than rarefactions, so the odd peaks are emphasized relative to the even ones. Matching that pattern pins down how much ordinary mass is present. The total matter density required to fit the timing and amplitude of oscillations is higher than that baryonic amount. The difference is assigned to the dark component. The numbers leave little room for ambiguity. There is more matter than baryons can provide, and the extra portion does not share the electromagnetic life of atoms. Subtler properties can be tested with composure. If the dark particles interacted strongly with themselves, they would isotropize and potentially erase central cusps in halos at late times. That behavior would feed backward into early clustering and alter the lensing deflection field of the ancient light. If the particles decayed with a lifetime comparable to the age of the universe, the loss of mass density would change the lensing amplitude and the late integrated contribution to large-scale temperature variations. If the particles annihilated with appreciable strength during the time of last scattering, the extra ionization from injected energy would broaden the surface from which the photons departed and blur the acoustic contrast. The calm map tolerates none of these alterations beyond tight bounds. Hidden complexity may exist, but it must whisper. Radiation density provides another lever. Additional light species would speed the early expansion, shorten the sound horizon, and shift the pattern of peaks. Some of that shift could be disguised by moving other parameters, but not all of it. The allowed room for extra light degrees of freedom is small when the glow is read carefully. That leaves the dark sector with a narrow hallway through which to pass if it wishes to be elaborate. A minimal cold component fits comfortably. Exotic additions must tiptoe to avoid leaving footprints that the data would expose. The distribution of power as a function of scale in the initial ripples also carries information about the silent mass. A smooth tilt close to scale invariance, when evolved through a universe with a cold, dark component, produces the measured hierarchy of temperatures and polarizations. If the matter were purely baryonic, radiation pressure would have washed away too much small-scale contrast before decoupling, and the later growth of galaxies would have struggled to catch up within the available time. A hidden reservoir that ignores light removes that obstacle. It stores contrast early and releases it later into the visible web. Cross-checks extend beyond the glow. The same sound horizon that sets the scale of the first acoustic crest appears as a preferred separation in the galaxy field. Converting between the early and late uses of that ruler, depends on the expansion history, which in turn depends on the total matter density. The value found from the sky's relic light sits in harmony with the value found from the sensors of galaxies when a cold dark component fills out the budget. A cosmos built only from radiation and baryons cannot maintain that harmony without slipping out of tune elsewhere. The quiet wait also helps balance two seemingly opposed demands. The early pattern asks for gentle differences during decoupling. The late structure asks for robust clumping across billions of years. Cold dark matter answers both. It stays withdrawn from pressure effects while the background forms, keeping the acoustic contrast modest. It then deepens wells as the universe expands, drawing baryons inward to form stars and clusters while preserving the large-scale smoothness that the relic glow celebrates. The result is a sky that wears two faces without contradiction. At millimeter wavelengths, it appears even and lightly freckled. In optical surveys, it appears wildly structured. One hidden ingredient allows both truths. Alternative scenarios invite inspection rather than dismissal. Warm varieties that blur small scales can be partially rescued with specific masses, yet the rescuing must be careful to avoid erasing features in the E-mode pattern. Self-interacting versions can soften galactic cores, yet they must remain nearly invisible to the ancient field. Mixed components with both cold and warm fractions can be tuned, but tuning competes with the clarity of the observed ladder of peaks. The relaxed nature of the glow is unforgiving. It tolerates many stories only if those stories bring their own quietness to the early stage. The elegance of the evidence carries an unexpected comfort. A component that does not radiate still opens a window into the first moments when radiation dominated the narrative. The path to knowledge does not require seeing the actor in a spotlight. It requires reading the way gravity writes in the margins of light. Temperature variations that rise and fall like a measured breath. Polarization patterns that fan and curl with decorum. Weak lensing that nudges lines into arcs. All point to a mass that keeps its counsel, and yet shapes the scene. No direct detection has yet lifted the dark into view, but the role it plays in the ancient canvas is specific enough to set anchors for future attempts. The mass must be sufficient to bring equality early. The interactions must be feeble enough to leave scattering to photons and electrons alone. The kinematics must be slow enough to protect small scales. The durability must be long enough to keep the mass budget steady through decoupling and through the age of structure. These anchors do not tell the whole identity, yet they narrow the field and give experiments a territory to search. A universe with a calm background and a stormy foreground can feel like a paradox. The paradox relaxes when the unseen weight is admitted. The calm is preserved because the light was allowed to disengage from pressure in wells that did not collapse too quickly. The storm arose later because those same wells waited patiently and then invited matter home. The glow carries no image of the dark itself. It carries the trace of the influence. In that trace is a portrait of an actor content to guide rather than to show. A faint wind moves through the early cosmos, not of air, not of light, but of particles too shy to linger, where interactions are frequent. They slip through matter almost as if it were not there, carrying momentum but rarely exchanging it. These are neutrinos, born in the first seconds when temperatures still crack nuclei apart and electrons met positrons in a fast ballet of creation and annihilation. They decoupled from the hot plasma when the universe was less than a second old, taking with them a memory of that era in their energy and number. Long after, when atoms formed and light began its quiet voyage, the neutrino sea continued to glide, invisibly present, shaping the background by gravity rather than by glow. Their presence is counted in an effective number that describes how much radiation they add to the early energy budget. 3 known flavors almost, but not exactly, become 3 units in that count. Subtle reheating when electrons and positrons annihilated raises the tally slightly. The value becomes a signature, not just of familiar particles, but of any whispering species that might have moved with the same freedom. If the count were larger, the young universe would have expanded more quickly. A faster clock would compress the time available for waves in the plasma to oscillate before transparency, shrinking the preferred sound scale. It would also lift the early horizon, shifting the delicate ladder of acoustic peaks towards smaller angles on the sky. Freedom changes more than tempo. Because neutrinos decoupled so early, they began to free stream across growing distances, carrying anisotropic stress that light could not supply while still trapped. This stress subtly altered the gravitational potentials in which the photon-baryon fluid was ringing. Potentials that might have remained still began to decay as radiation streamed. That decay advanced the phase of the acoustic oscillations. Peaks slid in angle by a small measurable amount. In the power spectrum, this shift plays like a musician leaning a fraction ahead of the beat, a quiet tell that neutrinos were already moving independently when sound was still crossing the primordial sea. Free streaming also blunted small-scale contrast. Where photons were chained to electrons by scattering, neutrinos flew unencumbered, smoothing perturbations beneath their large mean free path. Their motion left less gravitational pull on the smallest wavelengths, reducing the amplitude of high multipole power in a manner that attends the damping tail. The effect is modest, yet it is coherent and calculable. It folds into the same mathematics that governs diffusion damping, adding a signature that cannot be mimicked by ordinary matter alone. The calm fall-off at fine angular scales is thus not only a record of photons wandering before escape, it is also a record of neutrinos refusing to stay put. The background maps answer with parameters that describe this physics in compact symbols. An effective sound speed and a viscosity parameter encapsulate how a free streaming component should respond to pressure and shear in perturbations. Values near 1/3 for the squared sound speed and near 1/3 for the viscosity in the appropriate units match a gas of ultra-relativistic particles that do not collide after decoupling. Departures would have betrayed unusual interactions in the dark radiation sector, or a neutrino that felt forces beyond gravity. The measured harmony with the free streaming prescription extends confidence that the early universe contained a radiation bath behaving like known neutrinos. As the universe cooled further, the neutrino sea slowed. Mass, once negligible compared to thermal energy, began to matter. While still too ethereal to cluster like cold dark matter, neutrinos with non-zero mass suppress the growth of structure on scales below their free streaming length. The weight they carry is global, reducing the overall amplitude of matter, clumping at late times by a small but traceable amount. That reduction imprints itself on the lensing of the background, because less clumping yields a milder deflection field. By comparing the reconstructed lensing map to the predicted one for various sums of neutrino masses, limits emerge that press close to the thresholds set by oscillation experiments. The sky's oldest light thus sets hands on the scale of particle mass, not by catching a neutrino directly, but by reading the way gravity grew when neutrinos chose not to help. The same early count of radiation and the late influence of mass cohere with other quiet ledgers. Light element abundances forged in the first minutes depend on how quickly the universe expanded while nuclear reactions battled competition from the clock. A higher radiation density would have frozen more neutrons and shifted the balance among hydrogen, helium, and deuterium. Agreement between those abundances and the background's acoustic map makes the case that the neutrino census in the first minutes and at last scattering describes the same cast. Stability across this span of time leaves little room for extra players that behave like neutrinos without introducing discord elsewhere. There is a further timing mark hidden in polarization. Because polarization at large scales reflects the quadrupole of local radiation at last scattering, any shift in the phase and amplitude of acoustic motion from free streaming affects the crosstalk among temperature and E modes. The anti-correlation on degree scales gains or loses definition depending on how potentials decay when waves are midway through their cycle. Neutrinos add a nudge that sharpened this feature into the shape now measured. The shape is not only elegant, it is a test of the same story with different eyes. Beyond the background, neutrinos hint at a horizon yet to be reached. A cosmic neutrino background pervades space alongside the microwave glow, colder by a familiar factor that descends from the reheating of photons after neutrinos slipped away. That sea should bathe every cubic centimetre, with hundreds of near-massless travellers, today so slow that they are almost at rest in the quiet frame of the expansion. Direct detection would require a clever inversion of their shyness, for example by allowing them to be captured on tritium without an energy threshold. A successful capture would reveal itself as a small surge in electron counts, just above the end point of beta decay. The prize would be a first tactile touch of a background older even than the microwave light. Until such a touch is made, gravity remains the interpreter, and the background remains the book. Neutrinos also offer a path to test for new light species that left no other trace. A sterile variant that mixes faintly with the known flavors would contribute to the radiation count without carrying electric charge or participating in ordinary weak interactions at late times. Its footprint would be the same accelerated early expansion and the same phase shift in acoustic peaks. The allowed room for such a guest is narrow and has grown narrower as maps have matured. If a guest exists, it must be quiet enough to maintain harmony with the measured spectrum and with primordial chemistry. The serenity of this evidence frames the search for identity rather than ending it. The sum of masses remains to be pinned with a precision that rivals laboratory work. The ordering of those masses, whether one heavier state towers over two light siblings or two lie above a single light state, leaves subtle differences in how structure growth is affected across scales. Polarization at smaller angular scales and lensing, reconstructed with sharper noise properties, both promise improvements. Combined with galaxy surveys that trace the web in 3 dimensions, the influence of neutrinos can be triangulated from multiple vantage points. There is elegance in how these elusive particles enter the cosmic script. They do not brighten a single pixel of the ancient map. They do not announce themselves with spectral lines or with sudden flashes. They slide into the equations as terms that shape the rate of expansion, the decay of potentials, the phase of oscillations, and the amplitude of lensing. From those terms, a presence emerges that is as firm as any written in light. A universe that keeps such careful books is not hostile to subtlety. It welcomes it, and it records it with enough fidelity that patience can reconstruct the author. If a listener seeks a calming thought within this tale, it is this. The cosmos allows influence without spectacle. A ghostly sea that rarely touches anything still guides the timing of a drumbeat that became the framework for all later structure. The guidance is mathematical rather than muscular. The result is a pattern that could not exist in its measured form without the neutrino wind. To rest in that knowledge is to accept that quiet actors can govern outcomes, that what is not seen can be known through how other things fall into place, and that the first seconds left signatures gentle enough to ride the oldest light to this day. The sky carries a local hum that sits atop the ancient glow. Dust grains spin and beam along magnetic fields. Electrons spiral through the same fields and radiate. Ionized gas lets electrons drift past protons and softly shine. Galaxies far away but not ancient enough dot the microwave bands with compact light. Galaxy clusters heat electrons that bruise passing photons. Each intruder has its own grammar, a way of rising or falling with frequency, a way of curling or fanning in polarization. The task is patient disentanglement. The reward is a cleaner portrait of the oldest light, freed from the neighborhood's ornament. At low microwave frequencies, the main visitor is synchrotron emission. Charged particles, accelerated by magnetic fields, radiate with a spectrum that tilts downward as frequency climbs. The tilt is not uniform from place to place, because the energy of the electrons and the strength of the fields vary along the arms and spurs of the Milky Way. The pattern is bright near the plane, and along radio loops that arc like pale scars across the sky. Polarization is strong here, because the ordered part of the magnetic field imparts direction to the waving electric vectors. The sticks on a polarization map arrange themselves in long threads that trace unseen magnetism. A second visitor is free radiation from warm ionized gas. Its spectrum is gentler, closer to flat when written in brightness temperature. It is less polarized, since it comes from electrons that are deflected by ions, but not forced into coherent spirals. This emission fills H2 regions around young stars and spills between them in a fog. It is harder to isolate by polarization alone, so it must be separated through the shape of its spectrum and through cross-references to traces of ionized gas. At higher frequencies, thermal dust becomes the dominant foreground. Tiny grains warmed by starlight glow like embers, with a spectrum that mimics a blackbody colored by a power law in frequency. The temperature and the color index change with environment. Cold clouds in the outskirts glow differently than warm filaments near stellar nurseries. Dust also polarizes, because elongated grains align their short axes with the local magnetic field. Emission becomes stronger perpendicular to those fields, and the result is a polarized pattern rich with swirls and filigree. The same grains that comfort the night with faint infrared warmth complicate the microwave page with graceful but insistent strokes. Anomalous microwave emission sits between these regimes. It likely comes from very small grains spinning at tens of billions of revolutions per second, producing electric dipole radiation. Its spectrum arcs upward from low frequencies and then falls, peaking in the tens of gigahertz. Polarization is expected to be weak, though the degree varies with environment. The signal coincides with dust maps, yet refuses to follow the spectrum of larger grains. It is a reminder that the interstellar medium harbors several conversations at once. Point sources add freckles that must be masked or modeled. Radio-loud active nuclei shine at low microwave bands. Dusty star-forming galaxies brighten rapidly toward the submillimeter. Individually bright objects are catalogued and excised with circular masks sized to the beam. The faint tail remains as a nearly white noise background that lifts the small-scale power. Clusters of galaxies contribute through inverse Compton scattering. Hot electrons in cluster atmospheres upscatter photons, creating a decrement at frequencies below a particular crossover and an increment above. This thermal Sunyaev-Zeldovich signature appears as compact spots that can be identified and masked in temperature maps, or fitted and subtracted with matched filters that use the known spectral shape. To peel these layers away requires multiple colors. A single frequency cannot tell dust from glow or synchrotron from signal with any confidence. Instruments build maps at a suite of bands that stride from a few tens to a few hundreds of gigahertz. Each pixel on the sky becomes a small set of numbers as a function of frequency. The set is then analyzed with either parametric or blind approaches. Parametric methods assume a physical model for each component, with spectral indices and temperatures that are allowed to vary across the sky. The FIT returns maps for each emission, plus uncertainties that reflect degeneracies among them. Blind methods avoid a commitment to forms and instead search for combinations of frequency maps that minimize variance while preserving a target spectrum. Internal linear combinations are the simplest example, solved either in pixel space, in harmonic space, or in localized wavelet domains that respect both position and scale. Wavelets and needlets offer a natural language for this work. Foregrounds are not uniform. They are bright and structured along the plane and more delicate in the high-latitude sky. They are smooth on large scales and knotty on small ones. Decomposing the sky into overlapping windows in both angle and position allows the weights that form the clean map to adapt gently as the character of the contamination changes. The adaptation is bounded so that it cannot invent pathological structures in the residuals. The result is not a single answer but a family of clean reconstructions whose differences measure the remaining uncertainty. Care with polarization deepens the ritual. Bandpass mismatch can transform intensity into spurious polarization when foreground spectra vary across the beam. Small uncertainties in detector angles can feed true polarization into false curl. Beam asymmetries can imprint stripes or local patterns that mimic cosmology. Experiments respond with rotating modulators that separate sky polarization from instrument gain. with careful beam mapping on bright planets, and with cross-checking between detectors of opposite orientation. Null tests are the conscience of the pipeline. Maps split by time, by detector set, by scan direction, and by season are different to expose any structure that remains when the sky should cancel. Only after these trials do the cleaned E and B fields advance to science. Templates help. Low-frequency surveys trace synchrotron with high fidelity. High-frequency maps trace thermal dust with crispness. These external references guide fits in the intermediate bands that are richest in cosmic signal. The guidance is gentle. Templates are scaled by spectral models that allow spatial variation, and the fits are iterated with priors that prevent extreme swings where data are thin. Regions of obstinate contamination are masked entirely when the goal is a pristine measure of primary fluctuations. The masks are apodized to avoid sharp edges that would leak power across multipoles. Cross-spectra reduce risk. Instead of correlating a map with itself, which would square any residual systematics, analysts correlate independent splits. Half mission against half mission. Detector state A against state B. Frequency X against frequency E after foreground removal. The cross-treatment suppresses noise bias and reveals whether any stubborn foreground residuals correlate across channels in a way that could imitate cosmology. The power spectra extracted from these cross maps carry error bars that reflect both instrumental noise and the sample variance of the sky. Small mismatches remain, and they are catalogued rather than ignored. Dust polarization exhibits E to B power ratios that depart from naive expectations. Spectral parameters drift across filaments, revealing mixtures of environments within beams. Synchrotron indices steepen away from the plane. The decorrelation of dust across frequencies, a result of multiple temperature and alignment components along the line of sight, limits how far one can extrapolate a single template. Each subtlety narrows the lanes where blind separation is safe and encourages parametric models that acknowledge complexity without surrendering to it. The art of component separation is iterative. Maps are cleaned, cosmological parameters are inferred. Residuals are studied in the space of those parameters to see where foreground leakage could bias a conclusion. Masks are revised, weights are tuned. Additional bands are folded in from ground-based instruments that focus on clean patches with exquisite depth. External traces of gas, dust, and magnetic structure are cross-correlated to clarify which features belong to the galaxy and which to the cosmos. The process continues until the remaining foreground power lies below the statistical floor set by the cosmic variance of the signal itself. There is quiet satisfaction in the image of a sky gently unwrapped. A bright band is softened and set aside. Compact intruders are circled and removed. The remaining fabric is smoothed just enough to untangle local threads without fraying the ancient weave. What returns is not silence. It is a truer whisper of the oldest light, allowed to speak in its own register after the neighborhood's voices have been politely lowered. The act is not subtraction for its own sake. It is a way of letting the background keep its dignity while acknowledging the living galaxy through which it must be seen. New instruments arrive like careful listeners entering a quiet room. They lower their own voices, cool their hearts to near zero, and sit for long seasons with eyes fixed on the faintest traces. The goal is not spectacle. The goal is subtlety. A curl in polarization that might reveal the first tremor of gravity. A phase shift that might betray a new particle. A spectral bruise that might tell of gentle heating long ago. The craft has moved from proof into refinement, from broad maps into precision whispers. Detectors form the front line of this patience. Transition edge sensors balance on the knife point between normal and superconducting states, where a single photon warms the film enough to alter its resistance. Superconducting quantum interference devices convert that change into an electric signal with exquisite fidelity. Kinetic inductance detectors shift their resonant tones when energy arrives, allowing thousands of pixels to sing on a single readout line. Multichroic pixels divide light into several colors within the same horn, so each spot on the sky is heard across bands without moving the beam. On-chip spectrometers carve the spectrum further, replacing bulky optics with tiny circuits etched in cold metal. All of this rides in cryogenic chambers that cradle arrays at fractions of a Kelvin, because thermal quiet is the first requirement of listening well. Polarization control has learned new grace. Rotating half-wave plates modulate the sky's orientation into a frequency that electronics prefer, lifting it above slow drifts and gain wander. Variable delay devices switch angles with mechanical calm. Beams are mapped on planets until their shapes are known as carefully as landscape architects know their paths. Side lobes are fenced by baffles. Apertures are shielded from ground spill. Telescopes scan fields at many angles and speeds so that no artifact lives at a special frequency or direction. What survives this choreography has a better claim to being real. The sky is approached from 3 platforms. Balloons rise above most of the atmosphere and drift in stratospheric winds for weeks, carrying cameras that test technology and explore clean patches. They avoid the water vapor that clouds low frequencies and spoil polarization with rapid fluctuations. Ground telescopes settle at the high, dry rims of deserts and plateaus. Their mirrors grow to several meters so that arc-minute structure can be studied, while their receivers multiply so that the depth grows fast. Spacecraft leave weather behind entirely. They circle cold vantage points far from Earth's glow and gather light with uniform coverage that makes full sky statements possible. Each platform carries a piece of the program. Together they write a score that no single instrument could compose. The next decade favors breadth in frequency. Dust speaks loudly at hundreds of gigahertz. Synchrotron prefers tens. The relic glow sits between. Arrays now span 24 bands from roughly 20 to nearly 1,000 gigahertz, so that foregrounds can be modeled with room for their quirks. Broad coverage is matched to depth on clean fields, where thousands of hours per pixel yield microkelvin noise levels that let polarization patterns emerge. The design choice is deliberate. If a primordial curl exists at degree scales, it must be disentangled from dust filaments that curl by habit. Only a tapestry of colors can do that without assumption. Delensing has become a craft of its own. Lensing converts some of the clean gradient patterns into curl, masking whatever primordial curl might lie beneath. Maps of the mass between the last scattering surface and the present can be built by tracing the small-scale correlations that lensing creates in the relic field itself. They can also be guided by external tracers. The far-infrared glow of star-forming galaxies sketches where mass lies along the line of sight. Galaxy surveys draw the web in 3 dimensions. Each tracer helps reconstruct the deflection field. Subtracting the lensing B that is predicted from that field cleans the view and lowers the fog. The aim is simple to say. Leave nothing on the page but what the earliest moments wrote. Spectral distortions introduce a complementary sense. The ancient curve is so pure that even a small deviation would stand out with the right spectrometer. A tiny chemical potential-shaped distortion would tell of energy released long before atoms formed, perhaps by the decay of a light relic. A Y-type distortion would reveal how much later heating by shocks and clusters added to the photon bath. Damping of small-scale ripples in the early plasma released energy that must have warmed the radiation slightly, leaving a spectral scar that can be predicted. A cryogenic interferometer with absolute calibration could weigh these scars and place numbers on processes that the anisotropy maps cannot resolve. The observation is not trivial. It requires a stable view from above the atmosphere and a reference blackbody more perfect than any built before. The prize would be a timeline of gentle heatings that never rose to the level of chaos. Small scales promise another harvest. Arc-minute maps see the kinetic Sunyaev-Zeldovich effect, the slight dimming or brightening of the background as it scatters off moving clouds of ionized gas. That effect traces the winds of reionization and the growth of velocity fields that tie back to gravity. The thermal effect from hot gas in clusters becomes a census of formation histories and feedback from black holes. The lensing of the relic field by the Webb becomes a ruler for the total mass of neutrinos, since heavier neutrinos slow the growth of structure and soften the deflection field. Combining these measurements with galaxy surveys and with the preferred acoustic ruler tightens the net on parameters that describe both the young and the middle-aged cosmos. Designers have learned to respect the limits that nature imposes. At the largest angular scales, cosmic variance sets a floor under uncertainty. The only cure is to see more sky and to remove foregrounds with less guesswork. Full sky coverage from orbit remains the standard for statements about the broadest modes, especially in polarization, where the signal is weakest and the galactic veil is most insistent. For smaller scales, the cure is depth and cross-correlation. Independent maps are multiplied and overlapped. The same patch is observed by different instruments with different systematics. Cross-spectra are favored over autospectra. Truth emerges where methods agree while their errors disagree. The quiet energy that accelerates the present era is tested by these maps in several ways. The scale of the sound horizon, read from the relic field, is carried forward into the spacing of galaxies. The expansion history traced by that ruler and the growth history traced by lensing must tell a consistent story. Any drift from consistency hints at a change in how gravity works, or at an evolution in the smooth energy that fills space. The tests are not violent. They consist of small mismatches between curves that should overlay. The maps act as referees without raising their voices. There is room for surprise at the level of statistics. The relic field is nearly Gaussian, but not perfectly so. Bispectra and trispectra reach for faint fingerprints of interactions in the earliest fluctuations. A small feature in the potential that guided the first dynamics would leave a harmonic in these higher correlations. A gentle departure from a simple power law tilt would ripple into scale-dependent signatures. These are delicate searches that ask for sky with minimal contaminants and for noise that is both low and well-behaved. They are a reminder that the quietest lines on the page can still describe complex origins. The practical side of this pursuit is human. Teams assemble in deserts, on mountaintops, and in clean rooms where copper and niobium are shaped into lattices of sensors. They tune cryostats until helium vapor condenses on cold optics like frost. They align mirrors with lasers at dusk. They check readout lines for microphonic hum that might creep into data. They chase ground pickup by adjusting shields and scan angles. They write code that turns time streams into maps, maps into spectra, spectra into parameters. The tempo is measured in winters rather than nights, in flights rather than afternoons. The patience is part of the result. If the primordial curl remains hidden, the lesson will still be generous. Upper limits will turn into guides that select the most plausible early landscapes and push others aside. If a spectral distortion is not found, preferred bounds will fall on the amount of energy that could have been released without announcement. If small-scale lensing refines the mass of neutrinos, laboratories on Earth will gain a partner constraint that narrows the choices for hierarchy. Each outcome is useful. Each reduces the space in which the unknown can hide. A gentler vision also unfolds for the galaxy itself. Polarization maps reveal the magnetized anatomy of dust with a painter's delicacy. Cross-checks with starlight polarization and with radiosynchrotron deepen understanding of how filaments are threaded and how grains align. This knowledge turns from obstacle into asset, informing models of star formation and feedback while improving the cleaning of the relic field. The same data that polish cosmology also teach the neighborhood to describe itself. The horizon of ambition reaches beyond the next instrument. Concepts for future spacecraft picture a full sky spectrometer that could weigh distortions and polarization with the same calm authority that temperature once enjoyed. Designs imagine detectors that count photons across thousands of colors with quantum-limited noise. Plans include constellations that fly in formation to synthesize baselines larger than any single mirror, resolving small scales without surrendering sky coverage. These sketches are not promises. They are aspirations that keep teams honest today, because each step must prepare the ground for what the next step will require. The most relaxing aspect of this frontier is its refusal to rush. The oldest light will not flee. It waits with the same patience it has shown since atoms formed. Instruments can afford to be careful. Methods can be tested against themselves until the only surprises left are the ones nature insists on giving. There is no need to shout at the sky. There is only the need to listen longer, to cool deeper, to separate more gently, and to let what is faint stand alone. In that manner, the next notes will be heard, whether they are curls at the horizon, scars in the spectrum, or small changes in the way gravity writes in the margins of light. There is a shoreline where seeing ends and inference begins. The sky meets it in all directions. A round horizon, not of water but of time. Beyond it lies an opaque ocean of plasma that no photon from that age can cross. At this boundary the light is soft and constant, tuned to a temperature that barely stirs, patterned with ripples that breathe rather than roar. The presence is soothing. It is not a frontier of danger. It is a limit that comforts by existing, a reminder that some edges are gentle guardians of knowledge rather than iron gates. The horizon does not imprison. It defines. It says that the oldest reachable scene is a surface where atoms learn to keep their electrons close, where light began a pilgrimage that has not ended. Every direction is a different line through history, yet all lines arrive at the same luminous shell. There is relief in this symmetry. No corner is privileged. No path is denied. The same field touches every point of view. In that sameness, a listener can rest, because the background does not ask to be chased. It offers itself freely, day and night, regardless of season or latitude, indifferent to calendar and creed. Calm pervades the knowledge that the universe once held all places in close company. The smoothness of the field is not sterile monotony. It is a sign that conditions were shared before distance carried regions apart. The measure of that sharing is a near uniform temperature, a spectral curve without ornament, and a handful of statistical traits that repeat like motifs in music. These traits are not abstractions. They are expressions of a cosmos that found equilibrium early, then cooled with dignity. The effect on the mind is similar to snowfall that quiets a city. Structures remain, movement continues, yet the noise is softened and the pace becomes reflective. Within the serenity, freckles of temperature and polarization add character. They do not shout. They lean forward and invite attention. A degree-wide crest here, a smaller wave there, a slow anti-correlation between brightness and orientation that hints at a coordination older than the visible scene. The details are gentle in amplitude, yet large in consequence. They read like the steady handwriting of an experienced diarist, confident and unhurried. From them, a story of pressure and gravity unfolds that feels inevitable, as if the universe trusted its own equations to carry it from simplicity into texture. There is comfort in the way the field serves as a ledger. It keeps strict accounts of energy and matter, of invisible species that drift without scattering, of geometry that tends toward flatness by growth rather than by decree. The ledger is tidy. It rules out carelessness by refusing to bear distortions and by punishing impatience with inconsistent inference. In a world where many tales clamour without evidence, the background refuses melodrama. It offers norms and asks that hypotheses take their place in an orderly line. This steadiness is soothing because it honours patience and rewards accuracy. The horizon also frames humility. It declares that there is an earlier chapter obscured by fog. That admission is not frustrating. It is a relief. Mystery without boundary can be oppressive. Mystery with a clear edge invites interpretation without anxiety. One can study the ripples that reach the edge and deduce the quivering of fields before them. One can weigh the faint curl of polarization and infer whether gravity itself carried a tremor from a time when distances doubled like a breath. The inference is disciplined. It advances only where the map allows. The humility is earned. A subtler comfort arrives from the background's generosity. It participates in the chemistry of cold clouds by setting a floor under temperatures. It adds a constant to every laboratory that reflects radio waves or tests detectors, a standard that does not need to be carried into the room. It regulates the size of clustering by fixing a ruler that survives from pressure waves to galaxies, allowing geometry to be measured without reliance on fragile candles. A field this ancient could have withdrawn. Instead, it remains helpful, as if the oldest participant in a conversation chose to be a steady presence rather than a faded memory. The same horizon softens anxiety about scale. Many find the cosmos overwhelming because distances grow to metaphors that lose touch with experience. The background shrinks this overwhelm by being everywhere. Millimeter light gently bathes every surface, passes through walls, slips through human bodies without harm. The intimacy is factual rather than mystical. To be touched by photons launched almost 14 billion years ago is to be placed calmly on a timeline that wraps past imagining. The placement does not induce dread, it induces rest, because it confirms that existence is continuous and shared across epochs without drama. Quiet strength is visible in the way the field tolerates puzzles. A difference in the measured pace of expansion does not shake its stability. It creates a space where methods refine and ideas adjust. The horizon does not close because a parameter disagrees. It waits while instruments cool more deeply, while ladders of distance are rechecked, while new particles are considered or rejected. The background is patient because it has practice. It has waited since the fog lifted. It can wait a little longer for understanding to match its calm precision. There is a philosophy embedded in the temperature itself. A few degrees above absolute zero is a mood as much as a measurement. It says that violent beginnings can age into stillness. It says that heat can become history without extinguishing meaning. It says that a universe does not need constant spectacle to be generous with insight. The faint glow fills the dark not by overpowering it, but by offering a continuous baseline that makes every later light comprehensible. Against this baseline, stars acquire context, galaxies gain lineage, and time finds cadence. The horizon invites a particular manner of looking, not ransacking for breaking news in the sky, not demanding rapid answers. It invites the long gaze, the habit of returning to the same page and noticing a detail that had been overlooked, the discipline of subtracting the nearby to hear the far. That manner of looking is therapeutic. It quiets the reactive mind and strengthens the contemplative one. It is the opposite of panic. It is a slow walk along a shore where waves wash and recede, with a rhythm one can trust. Every presence eventually becomes background to something else. The oldest light is background to the theatre of stars, which in turn becomes background to the lives that unfold beneath them. The role is not lesser for being background. It is foundational. The field holds the stage. It provides the constant against which variations acquire meaning. There is deep comfort in recognizing that constancy is not static. It is dynamic balance, a steadying of the vast by the laws that tie energy to expansion, pressure to motion, shape to content. A listener can sit with this recognition and allow the mind to widen without strain. The oldest light approaches from all directions at once, without urgency, without favor. It tells a single integrative story that contains no heroes and no villains, only processes that operate faithfully across scale. The listener need not memorize parameters to feel the effect. The effect is a subtle slowing of breath, a reordering of priorities, a willingness to be instructed by what endures rather than by what shouts. The horizon remains a circle of calm around every eye. The glow remains a temperature that could be written on the edge of a quiet day. The small ripples remain, a script whose letters are both delicate and firm. From these, a universe can be learned without fever. From these, the restless heart can borrow steadiness. The lesson is not that everything is solved. The lesson is that nature keeps the most generous parts of its story, in forms that anyone can meet with patience, a curve, a temperature, a field that fills the sky. Night opens like a slow book. The first page is barely lit, a faint wash of millimeter light that has never been turned off. It moves through rooms and deserts, through the spaces between ribs, through forests shrugging off evening heat. It carries no message except presence. The presence is enough. It says that long ago the world was bright everywhere, and that brightness learned to relax. A breath steadies. The mind finds the horizon without travelling. It is a round boundary made of memory, stitched from photons that left their birthplace when atoms assembled from charged storms. The boundary is not a wall. It is an embrace. It holds a scene of ripples that will someday be cities of stars. It holds a spectrum that leans like a hill in winter. It holds a temperature that could be whispered. A reader of this light becomes a listener. Instruments can be set aside for a moment. Equations can be left humming on the chalkboard. The sky itself continues to offer its simple mood. Smoothness with freckles. Silence with rhythm. Distance with intimacy. In that combination, a person finds room to stand without shrinking. The oldest thing that can be seen is also the gentlest. If there is a promise, it is not of answers on demand. It is of continuity. The ancient glow remains patient while questions improve. It remains available while methods learn to be quiet in the right way. It remains honest while interpretation changes shape. The promise is that nothing essential in this light will betray the one who studies it, or the one who simply rests beneath it. The book closes without ending. The night keeps reading itself across the curve of the world. The background keeps its vow to be background. Stars move, clouds unspool, satellites wink and vanish. Underneath, the most relaxed fact persists, washing the edges of thought like quiet tide. The invitation is gentle. Sit, breathe. Let the old light finish its sentence.